So welcome everyone to the inaugural Against Breast Cancer Research Conference. It's a pleasure to welcome you all here today. So first I should thank Oriel College, Dr. Simon Lord for arranging this through Oriel to allow us to host this conference in this amazing venue, including the reception later in the College Hall. Today, before we get on to the talks, a few housekeeping issues. So for the talks, be 15 minutes. Just a reminder to speakers, Ali will give you the 5-minute remaining warning. So if you could leave a couple of minutes for questions, that would be great. I need to speak into this microphone, which I'm just about doing correctly now. A big thank you to everyone that's made this conference possible. I'll do more thank yous later. But we want to kick off today with a message from our founders. So many of you will know that back in 1993, Dr. Tony Leatham and Patricia Leatham established ABC after his observation as a pathologist of seeing far too many people losing their lives through breast cancer. And that started with a modest grant. And I will leave you in the able hands of Rob to give the welcome message from Pat and Tony Leatham.
Can I put that back in there? Is that okay? Okay. Yeah, that's going to work, isn't it? Excuse me just a second, everyone. Taylor Swift doesn't have these problems. Right. Good morning, everyone. It's lovely to see so many friendly faces. It's a real privilege to be here today, and especially to get the request from Anthony to read a few words that he's prepared. So, if you can just imagine, I'm a little bit older, a little bit bigger, and far more jolly than you pretty much get the picture of that's Anthony. So, hello everyone, and welcome. It's hard to believe it's been 30 years since Pat and I founded Against Breast Cancer. Our mission was to fund research into the treatment and prevention of breast cancer. Our focus on secondary spread and survival after diagnosis remains just as important today as it was when we began. Looking back, this journey we've been on together has been nothing short of remarkable. Some of us can remember when breast cancer was a topic rarely discussed, shrouded in fear and stigma. Thankfully, that narrative has changed, thanks in no small part to the creation of the iconic little pink ribbon. In 1994, the journey we were about to embark upon would challenge and inspire us in ways beyond measure. Never more so than when we launched our diet and lifestyle study. At the time, Diet Comp Life was the world's largest study into the effect of diet and lifestyle on breast cancer recurrence. Together, we have faced many obstacles, but through perseverance and the support of dedicated, generous people, we were able to achieve significant breakthroughs in understanding the complexities of breast cancer. Today, Pat and I are full of pride to see how far the charity has come. Thanks to highly talented, dedicated researchers, many of whom are in this room today, significant strides have been made in better understanding breast cancer. Early detection methods have improved, treatment options have expanded, and survival rates have increased, all thanks to research. Through you, Against Breast Cancer continues to play a crucial role in contributing to this progress. Pat and I are grateful to each of you for your help and for joining us on this journey. As we stand at the threshold of a new era in breast cancer research, I am filled with hope and excitement for what lies ahead. The present moment is characterized by unprecedented innovations in technology, groundbreaking discoveries, and as part of a global network of researchers, you are collaborating towards a common goal. We have witnessed remarkable achievements in early detection methods, and as personalized treatment approaches, we will witness improved patient outcomes. As we look to the future, our commitment to advancing breast cancer research remains unwavering. There is still much work to be done. We envisage a world where breast cancer is no longer a life-threatening illness, where every individual has access to the best possible care, and where no one has to face their diagnosis alone. By continuing to fund cutting-edge research projects, we strive to turn this vision into reality. I believe that by investing in education and innovative research initiatives, we can create a future where breast cancer is no longer a life-threatening diagnosis. With a patient's voice at the heart of our research, we can improve the quality and impact of our research. As we look ahead to the next chapter, we are deeply grateful for the unwavering support of this community, the dedication of our researchers, and the resilience of those who have faced this disease. Together, we can pave the way for a world without breast cancer. Thank you for joining us on this journey of hope and discovery. To each of our supporters, volunteers, researchers, and survivors, thank you for being part of this incredible journey. Together, we can make a difference and create a future where breast cancer is no longer a threat to the lives of so many. And to those who choose to join us, we say welcome to our community, where hope, determination, and compassion drive us forward. Thank you.
Fabulous, Rob. Fantastic message from our founders there. So without further ado, I will happily present the first talk. So Dr. Simon Lord is ABC Senior Research Fellow of Oriel College, Oxford. So the floor is yours, Simon.
Thank you for the introduction. So I'm a clinician, an academic clinician. I'm based up at the Churchill Hospital up the road, which is the main cancer hospital at Oxford. I lead the early phase clinical trials unit, and I'm particularly interested my main focus is on bringing new drugs into the clinic to treat cancer, in particular breast cancer. But I'm actually going to talk today about an old drug called metformin and how perhaps we can repurpose it for cancer treatment. I'm not going to, don't worry, I'm not going to deliver too much data. It's going to mostly be about a bit of a story, really. So, why might we want to, although my interest actually is often in putting very novel drugs into the clinic, why might we want to repurpose older drugs? Well, it's incredibly costly to bring a new drug from the lab into the clinic. The estimates now are to get a drug, a cancer drug, licensed at a standard care treatment from start to finish is about $700 million US. And that therefore reflects the costs that patients are paying in the healthcare system. But it's also the case that there have been some success stories to repurpose drugs cancer. Perhaps the most well-known one is thalidomide, which of course has a terrible reputation because in the 60s it was associated with severe birth defects that were used to treat morning sickness and in pregnancy. But then in the 1990s it was actually found to be an effective treatment for myeloma. Indeed, it was the first new effective treatment for myeloma in about 3 decades. And there are a number of thalidomide derivatives now used very routinely in the clinic, and they completely change the outcome. But going back to metformin, why are we interested in that? Well, many of you probably know this drug because it's so widely prescribed. Actually, it's been around since the 50s, and it's now the most widely prescribed oral anti-hyperglycemic, i.e. glucose-lowering drug worldwide. But there's been growing interest in its potential as an anti-cancer drug over the past couple of decades. And that's really was sparked by a series of epidemiological studies that suggested that patients with type 2 diabetes, if they were taking metformin, had a lower cancer risk compared to patients with type 2 diabetes taking other glucose-lowering drugs. And off the back of that, there are a lot of laboratory studies looking at metformin. Sorry? Can you use the microphone? Yeah, sure. Can you not hear it? Okay. Oh, online. Okay. So there are a number of laboratory studies, but also a few clinical studies that looked at the effects, in particular, of metformin on cancer cell proliferation. Typically in these studies, they give metformin for 2 to 4 weeks
after their diagnosis with cancer, and then take a surgical specimen and compare it with a diagnostic specimen. You can see for the diagnostic specimen, there's quite a lot of this brown staining, which essentially represents expression of Ki67, which is a very well validated marker of proliferation. And then you give metformin for 2 to 4 weeks, you look at the surgical specimen, and expression of Ki67 seems to be much less. And there are a number of these studies, particularly in breast cancer and endometrial cancer, that suggest there might be this effect in terms of reducing proliferation for metformin. And subsequent to that, there have been a lot of clinical trials set up worldwide. And we're actually now starting to get back a lot of the results from a lot of these big studies. And in general, they've been incredibly disappointing. So my life's work is, but anyway, we're still working on it. So one of them is the MA32 trial, which is probably the biggest of these studies, certainly in breast cancer, which recruited over 3,500 patients with early breast cancer. And patients were they were randomized to either have 5 years of metformin or placebo to see if this could reduce breast cancer recurrence. But the bottom line is it didn't. So there was no difference in survival between the two groups. I know that you hardly ever see something so conclusive or inconclusive, I could say, in that you can't see any. It looks like there's one line, but actually there's two there because they're overlying each other so perfectly. So there was no benefit to metformin in this context. Now, why did that trial fail? Why have a lot of the other studies failed? Well, it might well be, but actually when these studies were designed, we knew very little about the effects of metformin on cancer biology, particularly in the clinical setting at clinical doses. Most of the doses used in the lab are about 100 to 1,000 times greater than what you would see in the clinic at peak plasma level. We also hadn't really fully understood how perhaps we should select patients for metformin. That trial that I just showed you just selected any patient with early breast cancer. There were no real biomarkers involved. And we didn't understand properly how we perhaps should combine metformin with other treatments. Excuse me. What we did know from the lab was that metformin, at least if you use it at very high doses, is a mitochondrial toxin. There were a number of elegant studies that showed that it inhibits this thing called complex 1 of the mitochondrial electron transport chain. So in other words, it interfered with mitochondrial metabolism. Now, mitochondria are kind of the energy powerhouses of the cell, but they also act as a node to direct metabolism within the cell. And so laboratory studies, and it was proposed that laboratory studies showed, and it was proposed that metformin might reduce cancer cell proliferation by inhibiting mitochondria. Therefore, you disrupt the flow of glucose, and in particular carbons, molecules from glucose, to phospholipids and nucleotides, which are the key building blocks for cell proliferation. You also might cause an energy stress. As I say, mitochondria are the energy powerhouses of the cell. That will lead to activation of this thing called AMP kinase. So this is the energy regulator of the cell, if you like. And if AMP kinase is activated under energy stress conditions, it essentially wants to shut down the cell. So you stop producing new proteins, new fatty acids, which are all required for cancer cell proliferation. So there was this idea that it might have a direct effect on cancer mitochondria, but alternatively, others thought, well, perhaps maybe it has an effect on patient metabolism, and actually this is how it can reduce cancer cell proliferation. So the understanding is that in diabetic patients that metformin targets mitochondria in the liver. And this leads to activation of AMP kinase due to the energy stress, and this will lead to reduced glucose production. Therefore, reduce circulating insulin levels, which is obviously good in the context of if you've got type 2 diabetes. If you have reduced circulating insulin levels, you're going to stimulate the insulin receptor to a lesser degree on cancer cells, and that will lead to reduced stimulation of this thing called the PI3K pathway, which is a key driver of cancer cell growth, and therefore reduced proliferation. So it's kind of an indirect effect of metformin. So we set up a study to recruit 40 breast cancer patients, which we did successfully, in which we would give a course of metformin for about 2 weeks before they started their standard of care treatment. So these patients had sort of pristine, untreated breast cancers. And either side of this course of metformin, we carried out a series of pharmacodynamic tests. So we took some biopsies from the breast cancer before and after, and also in particular carried out novel imaging with dynamic 18-FDG PET-CT. Now, why were we interested in using 18-FDG PET-CT? So, we know that cancer cells take up a lot of glucose, in particular so they can proliferate, as I've described earlier. PET-CT can trace glucose. So essentially, 18-FDG is a radio-labeled sugar, analog of glucose, and it gets taken up to a greater degree into cancer cells than background tissue. And so we routinely use this technique to diagnose patients, stage them before surgery, for example, and you can also use it to monitor response to treatment. If you give metformin, the hypothesis was actually the cancer cells would respond by taking up more glucose because they have an energy stress. We also know that AMP kinase, if it's activated, will lead to increased uptake of glucose. And indeed, that's what we saw in our study. So you can see in this particular patient, before they've had metformin, we can't see any uptake of glucose into the lymph nodes in the axilla, the armpit here, but after metformin, they've lit up. And if we look at the primary tumour, after a couple of weeks of metformin, we got increased uptake of 18-FDG and essentially glucose into the tumour. So that was suggestive that we were seeing a direct mitochondrial effect. We also saw that there was a decrease in the levels of a number of mitochondrial metabolites within the tumour after metformin using a technique called mass spectrometry. So that was again suggestive that metformin was having a direct effect on mitochondria. And when we looked, we also looked at the expression of genes before and after metformin. We saw a lot of genes involved in metabolism that were up or down regulated, but in particular we saw a large number of genes involved in mitochondrial metabolism that were up regulated following metformin treatment, again suggesting that we were seeing a direct effect on mitochondria. So there is a lot more data to that study, but because I've only got a short period of time, I'm going to talk a bit about what we're doing now. So we're actually now interested in, I've told you about a lot of studies that have failed in terms of using metformin to treat cancer, but we're particularly interested in Oxford now with regards to investigating how we might use metformin as a cancer preventative treatment. Particularly in the context of this thing called Lee-Fraumeni syndrome. So Lee-Fraumeni syndrome is the commonest inherited cancer predisposition syndrome. So in other words, your lifetime risk of getting cancer is close to 100% if you've got Lee-Fraumeni by the time you're 60 years of age. It is caused by mutations in this gene called TP53. It's commonly inherited, although occasionally you can get sporadic mutations as well. Now TP53 is a tumor suppressor gene. So as long as it's functioning, it will put a brake on cell growth and cancer development. But if you lose the gene, as in Lee-Fraumeni, cell growth is somewhat uncontrolled, and you're much more likely to develop cancers. In particular, breast cancer is very commonly associated with Lee-Fraumeni. And part of this is down to the effects it has on metabolic reprogramming of the cell. So if you lose TP53, cancer cells in particular, they will upregulate mitochondrial metabolism, hence the interest in metformin, in order to funnel glucose carbons into the proliferative building blocks that they need. And a lot of work by this guy, Paul Huang of Met, who's based in the US, has shown that if you use metformin or other techniques to inhibit mitochondrial metabolism, you can, at least in mouse models of Lee-Fraumeni, where you've knocked out this gene TP53, metformin can increase survival and reduce the development of cancers in these mice. So we have recently got funding from the NIHR, so that's the NHS clinical research funder, to deliver a clinical trial where we test the hypothesis: does metformin reduce the incidence of developing cancer in these patients with Lee-Fraumeni? And we're going to recruit about 250 patients, but in the US, there's another study of similar design that's going to recruit actually slightly more patients than ours, funded by the NCI, so that's the equivalent of the NIHR. And we're going to understand, and we're going to, in our study and the US study, we're going to randomize patients with Lee-Fraumeni between 5 years of metformin and 5 years of no metformin. And patients are going to have yearly whole body MRI to detect new cancers, and also have regular blood tests to look for tumor markers. But we've also recently got funding to carry out translational work associated with this, which I'm leading, where we're going to take blood sampling, particularly mainly at baseline 12 months, but also actually on a yearly basis after then for the full 5 years. And here we're going to want to understand whether metformin's effects on insulin levels and metabolism links to any reduction in cancer incidence, but also whether effects on mitochondrial metabolism may link to any reduction in cancer incidence with metformin. But also, and lastly, we're going to carry out, we've got a lot of funding to biobank samples over the 5 years, blood samples, and we're going to then try and, in this very high-risk cancer population, try and identify new markers in the blood that can allow us to detect cancers developing early. And so that's it. I'd just like to thank all the people that have been involved in these studies, and of course our funders, including Against Breast Cancer, of course.
Thank you, Simon. I think we've got time for one question, if we have any questions from the audience, or potentially online. Here we go.
Hi, thank you. Really interesting. I should probably know the answer to this, but the dose that's used in diabetes for metformin, how does that compare to the dose you showed in that study in the animal models where you saw some survival benefit?
So in the Lee-Fraumeni?
Yeah. Yes, sorry, yes, in that last model.
So in animal models, they have managed I can't remember the exact dose, I'm afraid, and the equivalent. But mice seem to tolerate metformin better for some reason than patients. But I think that's a key part of the study that I showed earlier, that we are seeing at the doses we use clinically, that we do see an effect on mitochondrial metabolism. So we are seeing some of the same effects that we see in the lab models.
Okay, fantastic. Thank you, Simon. There's no further questions. Our next speaker is Oriel alumni and was a key member of setting up the first, being the fellowship program of Against Breast Cancer in Oriel. So I hand over to Professor Max Crispin.
Thank you so much. Hopefully. Here we are. So I've been asked to speak a little bit about the research that's undergoing in Southampton. But as Mark said, my journey with ABC really started with as one of the first Oriel Fellows, in fact, the first. So welcome to Oriel. I've been here for 25 years, on and off, but associated with the community, certainly for 25 years. Later on, we'll end up in the Grand Hall. You can see the Edward II at the front. So this is a College of Royal Foundation, founded in 1326, and where we're sitting here now is actually in an old real tennis court. So Charles I used to play here, was taught, and so yeah, fantastic. And you can see some of the old walls in the other room there, actually, as it happens. But really, the fellowships are fantastic because they really do, as this quotation says, the ABC Fellowship Scheme at Oriel firmly supports breast cancer research at the heart of the university. That was me saying that just now. What's really nice is it does mean that not only can we support very established research, you just heard from Simon, but also support people that would otherwise be potentially focused on other aspects. So, this gives us a research stipend to actually initiate breast cancer projects independently, and also by having the fellowships, it means that educationally, breast cancer specialists are interacting with undergraduates, do contribute to those educational schemes. So it keeps a new generation of scientists very much thinking about breast cancer. But I did transition over to Southampton then, in part because they had a new Centre for Cancer Immunology. So my research programme, where I was particularly focused on therapeutic antibodies, was really requiring the expertise that had been long established in Southampton. So I'm going to be representing a little bit of the work that was done in this building by Steve Beer's team, but you'll also hear from Charlie Burt's later and a number of the other researchers. But this was really quite interesting because they built this new building which under one roof had a clinical trials unit, lab spaces, office work, and various sort of preclinical units. And that's been really, as I hope you'll see, quite transformational going forward. When thinking about the research, the makeup of the programme, we do very much respect the sort of foundation of ABC and Tony and Pat's original vision. And what you'll hopefully be able to see is the intersection between modern sort of medical approaches and development of new diagnostics and treatment, but also very much linking to that diet and lifestyle theme. What are the impact of diet and lifestyle on things like treatment outcomes? So that will come very clear. So broadly, despite being a comparably small charity, it's great to see ABC covering these main themes of prevention, very much linked to diet and lifestyle, all the way through to detection and therapies. And of course, underpinned by the development of the biobank, which is in the process of moving to Southampton. So I'll represent one of those aspects, this development of therapies. Now, the art here, if you like, is that we have the development of therapeutic antibodies, and what we have is an intersection between, sorry, background stuff's been a bit messed up here. We'd have an iterative approach of design within this building where I'm based, the Highfield campus, and testing at the sort of cellular level up at the CCI. Now, to give a little window into our world for those who aren't based in a lab every day, this is the day-to-day life of our team, and we do things like manufacturing of antibodies by literally using cells to produce these proteins, so propagating cells and basically making them manufacture of antibody of interest. We show here in the middle protein production, so ultimately purifying out high quality, high grade material. And I've oversimplified it by saying quality control. That's a £1.5 million piece of equipment at the back there. Thank you, Bill Gates, for that one. It's a bit more sophisticated than just quality control. We can actually see novel features of the molecules, and actually it does help us redesign our molecules in many cases. Now, one particular well-established approach using antibodies to treat breast cancer is by targeting this molecule HER2, so this so-called HER2 positive breast cancers. And without going into all the numbers, if you look at the graph on the right, what you see is in terms of overall survival that there's a reduced survival with people who have this sort of HER2 feature. So very much the ethos in Southampton has been to look at the immune system as a source of potential treatment. We're not alone in that. This is now a massive, massive field. And this begins to show the sort of range of different options here, some of which you'll hear about later. I think Ben's going to be talking about some of the sort of peptide vaccines, for example. But I'll just focus on this particular features, using antibodies to target the cancer. Now, an antibody is made up of two main bits, this variable bit at the top and a constant region at the bottom. The variable bit, it means it sticks to its target, so it's sticking to HER2, not other things. Obviously, you want to recruit your immune system to those specific points, not widespread. You don't want to have autoimmunity. But this constant region is the bit that basically acts as a linker to recruit your immune system. And to give you another little vision of this, a bit more of a molecular, realistic sort of view, and actually it's highly flexible. So this is some EM work that we did on just a normal antibody and showed that this is highly flexible. And that's important for bridging the target recognition to immune recruitment. So what it does is it attacks onto your target molecules, your HER2, and then can recruit the immune system from various ways. Cellular, like white blood cells, macrophages, and also it can do activate soluble components of the immune system. Just focusing on one of those, I have to do a little click. It's a little movie that Steve has provided for me, showing that this process of cell eating. And what they've done here is they've just fluorescent labeled some beads and shown that macrophages and other immune cells can uptake the targets once they've been coated with an antibody. So that's one of the ways the immune system does actually eat and kill a target. Now, when we think about how to innovate in this space, I thought I'd scare you with this complicated graph. Because if you can think like, how does an antibody work? Well, it's got to bind to its target, fine. It's got to be able to recruit the immune system, fine. But there are other parameters that you can start to think of, and one of which I've been really interested in, is the impact of your existing antibodies. So you've got antibodies against flu or whatever, you've got loads, milligrams and milligrams in each tiny little volume of antibodies, and that actually acts as an inhibitor, competitive inhibitor. And what people did back in the 80s to show this effect was took red blood cells out of a patient, put an antibody against it, they radio-labeled the red blood cell, put it back in the patient, and depending on the level of existing antibodies, you have different clearance rates. And some patients have no antibodies, and when you compare the difference in clearance, when you don't have any antibodies, you get a rapid clearance of this red blood cell, and when you have antibodies, it's slower. So we know existing antibodies act as an inhibitor, and we also know, in more recent studies, that this does impact the efficacy of therapeutic antibodies. So on the left, if you have a high target density, if you have, in the presence of competing antibody, what that means, for the same level of killing, you need to add in a lot more antibody to get the effect of killing. On the other side, when you have low target density, which is often the case in these particular cancer therapies, even if you increase the amount of antibody you're giving, if you have competition, you never achieve full killing. So it can be a real barrier to effective treatment. So there's a number. This got us thinking about how this can be controlled, and one thing just to sort of make sure that we're on the right lines. If you take Herceptin, or this anti-breast cancer drug here, fancy name trastuzumab, when you can see the cell-eating ability is substantially impacted when you have competing antibody. So we know it's impacting this breast cancer drug. And just to show this more visually, normally you have an antibody. If you only get one or so molecules binding, you don't get response. You need a cluster of antibodies binding to get that recruitment. But if you have competition, ultimately it's less effective. So your antibodies literally bind to the cellular receptors of your immune cells and basically limit this effect. So one approach was to develop antibodies which had greater ability to recruit the immune system. And so we call these sort of tandem antibodies. And we had a number of different formats. This was done by ABC-funded student, now postdoc, Hannah. And the devil's in the detail here. We tried a number of formats. Only the one with a particular linker sort of worked. But this is very much what you can see. By bolting on this extra adapter region, we hope to actually increase the chances of recruiting the immune system through that noise. So, first things to do, does it mess up the ability to bind the receptors? And this is just a fancy way. When you see these curves going up, it means that we've got nice binding to the receptor. And what we can see is that by bolting on extra units, it's definitely working. In fact, the binding goes up. So then we can actually look at testing this. And what these next slides show is just a slightly slower walkthrough of the actual experimental basis on which we do some of the cellular testing. So what we do is we can label our targets with green dye. we can cover them with our target antibody, and then we can actually see to what degree are these targets taken up by macrophages, these cells, the so-called big eaters. And we can use fancy cytometry techniques. This is another big expensive box. What these graphs at the side really show is we can tell when there's no eating, so there's no green material inside these macrophages, or there's a little bit of green bit of eating. And in this particular extreme case, we got the whole cell taken up. And we can begin to measure the degree of eating of these targets. And the interesting thing is, well, yes, what we can show is by increasing this double linker, or these two adaptor proteins, the two FCs, we get increased cell killing. But importantly, most of the assays people do in the field don't add in competing antibody because these assays tend not to work. But in our case, because we've got this extra adapter, even in the presence of this competing antibody, we get to see that elevated immune recruitment. So that gives you a little window into how we're trying to redesign molecules, coming up with new ideas to be able to provide sort of better options for new therapies. So overall, you can see that the team does span a wide range of different aspects, and later on you'll hear a number of talks looking at that exact same molecule, like Herceptin, and how it is impacted by diet and lifestyle. So at that point, I think I'll keep the day moving on by leaving the stage very early, but I did want to just reiterate my thanks, and I know a number of supporters in the audience. We do try, and we really value everybody's support. The support that is given to the charity does go to labs and to researchers, supporting experiments, paying very modest stipends for students. It's really appreciated, and we'd really like to get involved in like the breast the walk ever. Those who've never done it, get involved. It's great fun. So anyway, thank you so much.
Right, do we have any questions after Max's fabulous talk?
Questions aren't compulsory. Hopefully it's not on real tennis or the rules of the tennis. Please, at the back. Oh.
Who had their hand up, sorry?
Is that Oliver?
I think there's a question here first.
Oh, okay. Sorry, thank you. Hi, thank you for a really interesting talk. Just a quick question, and I presume this will be part of testing if you develop this through trials, etc. It was just, you showed the increased binding to HER2. I was just wondering, do you have any impact on specificity with the modification?
Oh, that's the thing. So these really are quite modular proteins. So what you do at the one end, these adaptive regions, has no impact at all on where these antibodies bind. So we haven't changed at all the binding specificity, still binds to HER2. The only thing we're impacting with is the ability of it to recruit the immune system. There's the element. Actually, antibodies are themselves incredibly specific. So it's very rare for an antibody to go through development if it is binding to loads of other things and things. So generally speaking, that's not an area that we focus on too much on. That said, there's been a paper out recently showing that you can actually weaken the binding to certain targets. This paper coming out of Southampton, and actually can even enhance the ability of these cancers to kill. So you can engineer that, but our focus is just on the recruitment at the moment.
Thanks, Max. I was just thinking, can you you're using IgG in this case?
This is IgG, yeah.
So do you see that type of suppression by competition with other types of antibodies, so like an IgE, for example?
Interesting, because apologies, I have to answer this in a moderately technical way. So there's a variety of different affinity receptors, different affinities. So you have a panel of low affinity receptors here, and you have a high affinity one. That's really important. So Fc gamma R1, for example, is saturated. Normally the turnover is very low. IgE, that pattern matches-ish to that. So again, very low. So the competition effects are ferocious in the case of IgE, but it's also ferocious in the case of this IgG. Interestingly, we've also been looking at the use of enzymes from flesh-eating bacteria secrete enzymes to manipulate your immune system. You can use those enzymes to actually cleave all your antibodies and release that blockade to those high affinity receptors. So actually, by dealing with the competition effects, you can actually have different bits of the immune system which wouldn't normally be as responsive. So you can actually begin to engage Fc gamma 1 mediated immunity if you tackle the competition effects. So yeah, it's a really important topic.
Time for mine. I was thinking as you were talking, might another way around this problem to be actually to boost the macrophage function. So if you could boost, enhance phagocytosis, for instance, right? Even if you only have, low occupancy, low binding, you might still then get sufficient. I mean, if that is of interest, we should perhaps talk.
Yeah, I think that would be of interest, and I think the main thing would be to do it in a targeted way. So I think systemic activation. I'm not a specialist in this area, but I would be nervous about systemic activation of the immune system. Targeted in that environment, very much so. So yeah, fascinating area.
Okay, great. Sorry, were there any more questions? Oh, there is one. Yeah.
No, it was
Yeah, go for it.
Cool.
Thanks for the presentation, it was really good. I was just wondering, have you started to try and look at, with these antibodies, if it's also enhancing in, say, an organoid context, infiltration, and if on top of that, you're not getting polarization, say, if you're to M2 macrophages. I know immunologists hate that, but you understand what I'm saying in terms of it's actually having an effector effect on top of actually targeting the immune system.
Yeah, so I mean, the design is there to try and engage more with the effector cells, definitely. I haven't got any information about the precise macrophage biology that's induced, I'm afraid. But yeah, I think we will. This has been tested in a different system as well in terms of in vivo models against a lymphoma. There we saw it was very well tolerated, and you did see elevated efficacy. I don't know the deep biology in terms of the effects of it, but I think that'd be quite interesting. Yeah, sorry, you called me in an area we haven't yet to really properly investigate. Perfect. Okay, well, in that case, I'll hand over to Paul. So thanks so much.
Good morning, everyone. Firstly, I'd like to thank Against Breast Cancer, but I'd also like to thank all of you fundraisers and donors here, okay, because without you, we wouldn't be able to do what we do, okay? And what you do really in terms of your fight against breast cancer is actually quite awe-inspiring, okay? And I always say that, and it's really important because we just couldn't do this otherwise, okay? So, importantly is, why are we doing this? Okay, why do we do this? So the good news in terms of breast cancer is that, survival since the 1970s has increased from 40%, okay, so the 10-year survival rate has increased up to 80% today. Okay. Actually, 1 in 7 women are diagnosed with breast cancer in their lifetime. 55, in the UK alone, 55,000 women are diagnosed each year. But more impactful is the fact that we see 11,500 women's deaths a year and 85 men's deaths a year. So this is why we have to do what we do, because we want to bring that down, obviously, to zero. So Max talked about the ABC programme, he gave it an overall. So the ABC Discover programme is part of the Southampton ABC programme, and it actually impacts on all of these areas, so all of trade from biobanking through to therapy. So, for example, in early detection, we're developing biomarkers for the early detection of breast cancer, and you'll hear a little bit later after the break from Dr. Andrew Shapanis on some of the work we're doing with a new diagnostic test called MyOnco. We're also developing personalised vaccines. So what we're trying to do is improve the epitopes that we are able to discover so that it improves immunotherapies Hello? So that we can improve immunotherapies. And actually, we talked about eating cells, okay? So Dr. Ben Nicholas will be talking a little bit later about some of the work he's doing in that area to improve epitope discovery for personalized vaccines. But also part of this is we're really interested in how diet and lifestyle may reduce risk of recurrence or even development of metastasis. And underpinning this is the Diet Comp Life Biobank, which is here. And this is so we're using that. I'll talk about that in a little bit further, but it's really to understand why some cancers become metastatic, identify risk biomarkers of recurrence and metastasis, and obviously revolutionize better treatments. So the team are part of the ABC Discover. So we have Dr. Andrew Trapanis, Dr. Ben Nicholas, and Max. But we also have Lewis Coy, who's a PhD student. He couldn't be here today because he's just finished his thesis and he's defending his thesis on Friday. So he's otherwise engaged and focused on other things. So he didn't really want to come today. So Diet Comp Life Biobank. So this was funded by Against Breast Cancer. And this was designed to investigate diet and lifestyle factors that affect the risk of secondary breast cancer. So there are over 3,000 patients, breast cancer patients, enrolled from 56 hospitals across the whole of the UK. And biological samples and diet and lifestyle questionnaire data were collected over 5 years post-diagnosis of breast cancer. So for that type of data and those types of biological samples, it's one of the largest collections of its kind. And why it's important is it's important that we be able to study differences between patients that go on to develop secondary breast cancer and those that don't. So the ABC Discover, as I said, we collected, there's a large number of biological samples collected, so 48,000 serum samples, 91,000 urine samples, okay, but also this diet and lifestyle information. So these were full questionnaires of all of their diet and lifestyle throughout the whole of that 5-year period, which is extremely nice. And the idea of the ABC Discover program is to use in-depth technologies, which I'll talk about in a little bit more, to be able to characterize those samples from the Diet Comp Biobank, understand why some cancers become metastatic, identify risk biomarkers for breast cancer recurrence, also for early detection of breast cancer, and also to be able to revolutionize better treatments and testing for patients. So the technologies that we use, okay, Francis Crick's central dogma is that DNA goes to produce RNA, goes to produce protein, okay. The field of transcriptomics measures RNA and their expression levels. The field of proteomics measures protein expression levels, okay, their amounts. And metabolomics measures the small molecules that are produced by those proteins. It's the field of metabolomics. And what we're doing with the ABC Biobank is using all of these technologies to measure those samples, okay, to measure the RNA level, protein level, and metabolite level, and integrate this together with other information, such as clinical and physiological data, and of course, patient outcome data. And the idea being is that we can generate phenotypes and identify phenotypes of individuals about whether one, for example, in terms of their outcome, okay, prognosis, about whether they may go on to develop have recurrence or go on to develop metastatic disease, but also about how that diet and lifestyle can influence that development of metastatic disease or recurrence. Now, this is actually quite a challenging problem. It may seem like it's an easy problem, okay? But when you generate all these large data sets, which we're very good at being able to do, the able to interrogate that in an unbiased way can be quite challenging, okay? Because traditional statistics doesn't work particularly well in these contexts. So therefore, in my group, we've developed something called topological data analysis, okay? And topology meaning shape, okay? And the premise behind topological data analysis is that data has a shape, and that shape has a meaning. And there's a lot of mathematical functions that sit behind this, but I'm going to try and explain it so that it's really sort of hopefully clear. Okay? So this is a line graph. You may be familiar with a linear regression plot, okay? And indeed, a line is a shape, okay? And of course, if you knew x, okay, you could predict y, and vice versa. If you knew y, you could predict x. However, if you had something like this, you couldn't faithfully draw a line through these. What you could do is you could maybe use something called a clustering algorithm, okay, and cluster those into groups, okay, into separate groups. And that's another algorithm. Then you may come across something like this, these data. Okay, so this is typical of what we would call periodic or recurring data. And so you can develop another algorithm to be able to interpret that, to analyze these types of data. The problem is you can go on generating infinite numbers of data analysis approaches to be able to interrogate it. And this is where topological data analysis becomes very useful, and a useful tool in being able to interrogate the data. So, another analogy, if you imagine a hand, and you imagine that as a point cloud, so every thermal imaging camera, you could put a thermal imaging camera across that surface, and here we have fingers which are hot and getting cooler as we approach the wrist. Yep. Then do some level of data reduction, okay? And so we can chop the hand up, okay? So we have fingers, we have knuckles, we have the thumb, and we have a wrist. We can then represent that as what we call a network, okay? So here, each of these nodes, okay, here, action. Now what we have is we have a hand, which is represented as a network graph, with additional information. And we can do the same with any type of data, or majority of data. So this is actually not a cancer sample, okay, a cancer network. This is actually from asthma, okay, but it's just a nice one to look at. It's actually severe, mild, and moderate asthmatics. We've done the same approach, but then we've actually applied topological data analysis to stratify that patient cohort. What you can see here is we have these groups which are very nicely defined on the picture, okay, and these represent, so those which are close together represent very high similarities, so this group is very similar, and they're very different to, for example, the groups over here. And so we're able to stratify that patient risk. What we're also able to do is we're able to map on top of that different colours of different features. So we could start to map on, for example, clinical data onto top of that. We could start to map on pathway data onto that. Okay, so we can start to interrogate these structures in depth. Similarly, what we did is we took, we've given access to something called the Metabrick cohort. Okay, so this is data from over 2,000 primary breast cancer tumours. Okay, thank you. And so this had transcriptomics data. Okay, we combine that with our clinical and physiological data to generate this network graph here. So here we have a network graph. I'm not going to go into it in too much detail, but just to say, for example, this group down here is seen highlighted in red. Each one of these nodes represents a patient, the patient's tumour. You can see that these here are those that have a good prognosis. As you move up to the top, we have those which have a mediocre prognosis, and those down the bottom right here you can see have a bad prognosis. So we're able to stratify the patient population here in terms of prognosis. Then what we can also do is we can then look at those clusters and start to actually dive in depth with those clusters and start to look at what, in terms of the molecular phenotypes, actually underpins. In other words, what genes, what proteins are actually representative and indicative of those phenotypes. And indeed, in cluster 1 here, okay, which is the poor outcome phenotype, then what we actually see is, for example, is angiogenesis, which is very important in terms of tumour growth. That tends to use the oxygen consumption, hence we see high. Also, for example, the epithelial mesenchymal transition, EMT, we see that this is noted in cluster 1, okay, and this is important in motility and invasiveness of the tumour. And we can see in cluster 2, which was the mediocre, we can see that we see less markers associated with angiogenesis, still see markers associated with the EMT. Then as we move to cluster 3, where we see the good prognosis, then we can see that these markers of angiogenesis and hypoxia down. So these are the ways in which we can interrogate the data. All of the DIACOM biobank, and then to interrogate that in the same way to define the phenotype and try to understand, one, in terms of metastasis, also about how diet and lifestyle can impact that. Okay. So I wanted to just quickly mention Lewis's project. He couldn't be here, unfortunately. So Lewis's project, you know, as we've heard earlier, is that drug discovery is very expensive. Okay. To do drug discovery through to the clinic, okay, and it's very slow. It's around 10. During that process, you see, what you're looking to do is to take your targets from discovery through to preclinical. And it's not really to see which ones are successful at the preclinical stage, it's to be able to fail those which aren't going to be successful very, very quickly. Okay, so you can basically discard them and then move through your big candidate. Okay? And in fact, the success rate of oncology clinical trials is as low as about 3.4%. But therefore, better clinical models potentially can improve clinical trial success. And so Lewis's project was about comparing what's a standard sort of 2D culture systems, 3D culture systems, okay, which are potentially more representative of tumours. One of the challenges is in terms of triple negative 3D culture systems, if you look at the literature, is they're not very well characterised, and the molecular mechanisms that underpin these compared to 2D to 3D, the data is just not there. So we need to really understand whether they are representative or not. So here's a representation of a 2D culture system, so you can see the cells here on this monolayer, and then in a 3D, we have these what's called ultra-low adherent wells. They don't bind to the surfaces, and they form these clump of cells, okay, called a spheroid, which looks very similar to tumour. And the advantage of these is that you can actually do high-throughput drug screening, because you can have a 15-3-6 well format. You can screen 15,000 compounds an hour, 100,000 compounds a day, and so therefore your preclinical can be very effective. But understanding whether these models are actually representative of the tumour is important, and so that was part of Lewis's project, as was. So what he did was he was basically creating, the same as we talked about before, we talked about handprints. Okay, so he used transcriptomics and proteomics to create a handprint of both the 2D and 3D systems to compare those. And he then also looked at the effects of the two most key chemotherapeutic agents used, doxorubicin and paclitaxel, okay, and looked to see the effects of those on the 2D and 3D culture. He showed that in the triple-negative breast cancer 3D culture, the model was less sensitive to doxorubicin and paclitaxel than 2D culture. Importantly, he then performed molecular phenotyping of these two and identified key pathways for both chemotherapeutic agents specific to the 3D culture models. And it's also providing potential insights into drug resistance mechanisms, which are currently. This on the side here is just really, I don't expect you to look at this, but really these are some of the pathways which are identified from the proteomics, okay? The red indicating that these are down-regulated, the green representing that they're up-regulated. This has these across all of the therapeutic agents, and not only at the transcriptomic levels, the RNA level, it also has that at the together. So just to summarise Lewis's work, is that in-depth molecular characterization of the triple-negative breast cancer 3D culture model identified 3D model-specific pathways, which you might expect. Okay, they look like that. He's also done comparisons to expression data in tumour, and they look very similar in some aspects, not necessarily equal aspects. And molecular phenotyping of these therapeutic agents and 3D culture models provide insight into possible therapy. Further analysing the data, and the publication is almost being submitted today, I think. Okay. So, thank you very much for that. Thank you.
Any questions from the floor before we go to break?
Hi, thank you, Paul. Really interesting. I mean, it's a great resource, the study. Could I just ask, because it wasn't clear to me, so do you have access to the paraffin blocks from the original tumour tissue, and what's happening by way of ongoing follow-up? Because for breast cancer, 5 years follow-up is quite short, and obviously.
So DICOM life is very much about biological fluid, okay, and not tumour tissue. We are following up, so we have an application into NHS Digital. Now follow up. Sorry, so we're following up for 10 years. In terms of paraffin blots, not as part of Diet Comp Life, but a part of another study that, that Tony Leatham had many years ago, is he has actually naive patients. So he has a lot of paraffin blots from naive patients who were then treated subsequently to that, which we may actually use as a potential resource. It would be nice to have the tissue if we had the matched tissue, but we don't have that matched tissue.
Right. Thanks very much, Paul, for a fascinating talk. And now we go into the break, which, if you haven't seen, is through into the seminar room. If everyone could be back in their seats by 11:30, please, for the next talks. Thank you. Okay, everyone, if you could take your seats, please, so we can keep to time. So for the next session, if I can remind speakers if they could speak quite closely into the microphone so those online can hear. So without further ado, I will introduce our next speaker, Dr. Andy Sopanis, who will talk about onco.
Thank you very much. So yeah, thanks for the introduction, and I just want to start again by saying pretty much what everyone else has said so far, that none of this can happen without ABC. So we are genuinely very, very thankful. So I'll be talking about myonco, which is a multi-cancer early detection test. So I think everyone in this room is all too familiar with the problem of cancer. And I think everyone here probably also knows that half of all people will suffer from cancer at some point in their life. But what people don't necessarily understand or know is that half of those cancers are quite often identified at a late stage where survival rates can be below 10%. These same cancers, however, if we can identify them at an early stage, they can have survival rates of over 90%. So there really is a need for early diagnosis, and I think everyone here does understand that. The problem is that current early diagnosis is reliant on screening assays, but these do still suffer from several key limitations. So firstly, they're only available for breast, bowel, and cervical, and they can only test for one of these types of cancers at a time. They also can have quite low sensitivity at the early stages, and importantly, they have a low specificity, which means they have a high number of false positives. In fact, 1 to 18 here in the UK, so for every one cancer they correctly identify, we incorrectly say 18 people have cancer when they don't. And so this is why we've developed what we're calling myonco. It's a play on words, and I can come on to it later. But essentially, we use microRNA, and it is a blood-based multi-cancer early detection test. So what we do is we take just a small amount of blood. It's 100 microliters, so it's, I think it was about 12 drops of blood, because we need the serum, not the whole blood. And we use our panel of microRNAs. microRNAs are small RNAs. They regulate expression. They can help have a big downstream effect and regulate what happens in the cells. And we have a panel of 50 of those that we measure. This is where the myonco name comes from. My, micro, onco, cancer, my cancer. And we use AI, nice fancy word. Really what it is machine learning prediction model. So we've trained it on data. And again, I'll come on to this on over 20,000 patients. And we use it to predict the unknown cancer patients or the unknown patients. Ultimately increasing survival. That's the whole goal of this. So the way that we developed myonco, like I said, it was on 20,000 patients, on data from 20,000 patients, spread across these 12 cancers, of which breast is there, of course. And what we did, without going into too much technical details, I want to keep this quite light in terms of the technical, although there are a few graphs. We split into train, test, and validation. And so within the training cohort, which is 14,000 patients, we used a number of different methods to identify the most predictive microRNAs, because some of them are not necessarily indicative of cancer or predictive of cancer, so we identified the ones that are best at predicting it. And then using those 50 that we had, we plotted them on those 14,000 patients, and you can see that cancer patients separated out from non-cancer patients quite nicely. You know, there's quite a nice sort of divide there. Obviously, there are some in this group, and very few actually, but in this group. But this was using a very rudimental tool called principal component analysis. We use this quite often. It's quite simple. So what we wanted to do is take it a step further and really try and get as much out of these microRNAs as we could. So we created 2 machine learning models. One, a support vector machine, it's a type of algorithm, and then a neural network that I think probably everyone is more familiar with. Firstly, to predict, is cancer present? Yes or no? And then if it is present, the neural network then says, okay, where is it located? Where of those 12 cancers that we can identify is it located? So we developed the models, and then we tested them on the test and validation cohorts. And these are ROC curves, receiver offering characteristics curves. Don't worry, basically all they are is you have sensitivity on the left, which is how many times you can find it and it's actually there, and the specificity, which the false positive rate, essentially. And when we're detecting cancer, no cancer, we have almost a perfect sensitivity specificity. So we have really great accuracy of identifying if cancer signals are present in a patient's blood or not. And this is across all stages. So that's the important part, right? We need to be able to identify it early. And then the tumor site of origin, that is, where is it located? We have an AUC of 0.99, so basically an accuracy of up to 96%, depending on the cancer type. And these results were echoed in the validation cohorts, and the validation cohort is another standout cohort. So it's an independent cohort, like the test, but it's just another separate holdout data set, so we can prove that it works not in 1, but 2. And the same results are seen. I'll just highlight that although it says 1, which is a perfect score, it's rounding up, there are still a few misdiagnoses, which is kind of a good sign every now and then. So how it works, essentially, I've spoken through it in sort of brief, and I'll go through it again in brief, but I'm sure there'll be questions later. So microRNAs are released by, and this is our panel of 50, by the tumor itself. So as the tumor grows, it changes, and it changes in ways that aren't normal for normal cells, and so it's spitting out different amounts of profiles or different amounts of microRNAs than it would normally. But then also the healthy cells around the tumor, so if this is the tumor here, the healthy cells around it are putting microRNAs around the microenvironment, which you've heard of today, to try and counteract some of those differences. And then there's also, well, the tumor microenvironment in general, which sort of gives us the first indication, right? Because as the cells start to grow, as the tumor starts to form, it will change the environment itself around it, and we're picking up signals of that as well. So these start to circulate the blood. We extract the blood, we extract the total RNA, and then we extract the specific biomarkers that we're interested in. We then we quantify them in a few different ways. So mainly at the moment, we're focusing on quantifying qPCR because it's cheap, it's fast, it's scalable. If we can get into a qPCR format, it really can become a screening test that can be done at a population level, and that's where it's going to have the most benefit to patient lives. So we measure those 50. We then normalize them using a number of internal controls to make sure that normalized and standardized. And then we use those to predict first if cancer is present, and then if it is present, where it's located in the body. So there are a few different methods of doing this, and there are other sort of, we may have heard of the Gallery trial from Grail. So the Gallery test is currently being trialed in the NHS. It's a great step forward to early diagnosis. But the problem is that they, along with many others, use circulating tumor cells or methylated DNA. Without going into too much detail, this is basically a direct marker of the cancer. So the methylated DNA comes from the cancerous cells, and circulating tumor cells obviously also come from the cancer cells. So as the cancer gets larger or more developed, you get a higher signal. But at the early stages, there's quite low signal, so the sensitivity is quite low for the early stages. You can see this in a lot of the other sort of solutions here. But with MyOnco, because we're measuring microRNA expression, we have the signal throughout. There is signal, and it's more about the profile that tells us if cancer is likely present, yes or no. So the signal remains high throughout the early stages, and that's why we do have great sensitivity, and this is in the test and validation, across the different stages. So I spoke a little bit about how we developed it and what it was done, but I never really said the impact that it could have. So MyOnco can target 12 of the most prevalent and lethal cancers, so that's roughly 68% of all new cancer cases. Obviously, breast is in there, as it's one of the top ones, or is in females, in one single test, right? So this is one blood draw, one test to hopefully identify those 12 cancers if they're present or not. with a high sensitivity, you saw that in the previous slide, and importantly also a high specificity. If this is going to be a screening test, if we really can get it into the NHS to be used at population level, we want to make sure that we aren't giving false positives. One, it costs a lot of money, but two, it's a huge amount of stress for a patient, right, to be told you may have cancer and then, oh, sorry, you don't. That's obviously something we really need to avoid. So the potential impact of MyOnco, of the 990,000 cancers, that MyOnco can target in the UK and US, unfortunately around half of those will currently die over a 5-year period. But if MyOnco was used in a whole population screening setting, then hopefully, we could save over an additional, I can't remember, 300,000 lives. Obviously that's at a full population level, but it's, it shows the true impact of what it could have. So where we're at currently, the data you've seen is obviously where we're currently at, but we've also got, I would like to say the grants, what they are, but they're still under embargo, so we can't, and with the election coming up, we can't actually go to say who they are. So later on we will, but we had £100,000 from a government grant and a £2.4 million from a government grant. And we also have a partnership forming with a company called UC. They specialise in qPCR kit development, so they're going to help us translate it into that qPCR setting, the ideal format. This grant is to advanced development, so working on ways of changing the chemistry in the qPCR to try and get it as more sensitive as possible. This is working on optimization, kind of like the throughput, really getting it to a stage that it can go to a population level, and then further validating on a brand new cohort, a new 8,000 samples, hopefully stretching from the very early stages of cancer, so pre-symptomatic, which is where it will be in the screening setting, all the way through to stage 4. And this is just some action shots of our employees in. So this is where we see it now. This is what it is. But we do think that the microRNA sort of target, or the panel that we've got, along with other research that we're doing, can be used in a number of different areas. And in fact, we are starting to look at other areas. So it's important to understand, okay, they're predictive, but why? What are they doing? What's the underlying biological function that they're having an effect on? That will hopefully lead into therapeutics, everything else. And then obviously recurrence is going to be important, as well as cytometastasis. And that's where sort of the biobank comes in, the DICOMP Life Biobank. So you heard from Paul that we have thousands. There are hundreds of thousands of samples stretching from patients across, telling us about their diet and their lifestyle, and about their occurrence. So, if we can use that to try and identify markers or try and understand what is causing the recurrence or the metastasis or whatever else, it's going to be a huge leap forward. So this is going to help us also, hopefully, help identify characterize the biology and also the recurrence going forward. So I think that was quite a quick whiz through, but again, I just want to thank you, but also thank you all for coming, because really it's quite nice to show off some of these results. And I think that it's a great time for us all to get together, and again, thank ABC for what they are doing, because it is hugely impactful. Thank you.
Amazing talk. Terrific talk. Thanks, Andy. I'm sure there'll be some questions.
So thank you very much from a survivor, a mom of 2 girls, and a social science researcher, from which comes my question now. In terms of your sample, what of patients, do you have good results in terms of the underrepresented groups that are often the ones that they have a limited uptake in screening and activities, and where the potential for such a test might be amazing?
Yeah, so at the moment, I'll be honest, we don't have the age data of these patients. We don't know how the split across the ages. They'll typically be the older generation. Like you said, they're quite underrepresented in a lot of studies. And so unless you oversample and enrich for that patient cohort, you don't have them. We are hoping that, so with some of the cohorts, some of the samples that we're going to be using in the next validation trial, it's basically done. One of the studies, they went around just random locations in supermarket car parks, and they just recruited people. This was during the days. The majority of those will be, again, probably more retired, but hopefully there will also be some younger ages in that cohort as well. But it's true. I mean, it would be nice to prove that it can work in the younger cohort, in the younger patient cohort as well. But I think that needs to happen as a complete study, right? We need to make sure that we design it specifically for that purpose, because it is different in itself.
Thanks, Andy. That was great. I was just wondering, you mentioned the issue with circulating DNA and potentially picking it up too late. Why is mRNA any better?
Yeah, so, I mean, it's a hard question to answer because it depends on. So the methylated DNA is obviously it's going to have high specificity, right? Because it's coming directly from the cancer. But with microRNA, you're always going to have microRNA signals. You're always going to be able to pick up the microRNA. It's always going to be there. Like in a healthy patient, in a whatever patient, there's always going to be levels. So it's more about the profile. It's more about the relative differences between that panel of 50, which is indicative of, in this case. Kind of answer.
Thanks, Andy. So first question is, so this is a test you've developed, so people will send you blood samples and then the lab would run it. Are you looking to automate it?
Yeah, so for the ultimate use case, a screening test, that's where, like I said, it can have the most benefit. It needs to be highly automatable. And so we're trying to build it into a liquid handling system. So you're familiar with liquid handling, right? It's all the pipetting sort of manual steps taken out, and then you also reduce the variability. So yeah, it's higher automation friendly as possible.
And as a standalone desktop unit, could you get it to that? No.
So there's no real need for it because we're using qPCR, which is a really standardized approach, right? I'm sure most people even know of it from COVID, right? You send a swab off, you get it off. It's highly scalable, cheap, high throughput. If we do it in that format, there are loads of qPCR manufacturers. So we don't see the point in manufacturing a new device when their current devices can work. It's more about you measuring those microRNAs and then using our prediction algorithms to detect if cancer is present or not. This reduces the burden on.
The risk of errors. Another question was, you mentioned what stage of cancer, but then later on you didn't mention that in the sampling. Can you still determine from the mRNA what stage the cancer they're at?
So we don't determine the stage. We can just get it at early stage. We haven't really looked to see how well we can predict the stage. And it probably is important clinical information for the clinician to know. But in this case, we just wanted to prove that we can find it at stage 1 or stage 3. Yeah.
Thanks, Andy.
Thank you, Dr. Shapanis, for an incredible talk. Right, maybe we have a bit over time, but there's a lot more time for, I'm sure there'll be many more questions because the Marco test is incredibly exciting. So I'd like to introduce our next speaker, research fellow for the ABC Oriel program is Dr. Lena Hacker. So.
Okay, thank you so much that that I can speak today, and also for all your amazing support. I'm so grateful to be funded by such an amazing charity, and it's really great to also see so many of you here. So my name is Lena, and I'm the new Junior Research Fellow on the ABC program, and my research is focused on developing new imaging tools and strategies for the early detection of breast cancer. Now, one of the key characteristics of all solid tumors, including breast cancer, is tumor hypoxia. So when we talk about hypoxia, so hypoxia refers to low oxygen content in tissues, and this is caused by the proliferation of cancer cells, and then they outgrow the existing vascular supply. But when we talk about hypoxia, we often refer to chronic hypoxia, so the constant state of low oxygen. But there's also a phenomenon which is called cycling or perfusion-limited hypoxia, and this refers to variations in oxygenation that are caused by temporary local disturbances in blood flow. And these variations can occur in different frequencies, ranging from minutes to hours. Now, it has been shown that tumors that exhibit this cycling behavior and oxygenation are more resistant to radiant chemotherapy, have higher metastatic potential, and also have higher intratumoral inflammation. And overall, this leads to poorer patient outcome. For this reason, it is very important that we understand why these fluctuations occur, and also whether we can use this information to adapt treatment regimes. So one novel imaging modality which has very high potential to look at these dynamics is photoacoustic imaging. So photoacoustic imaging is based on the conversion of light into ultrasound. Essentially, we shine short laser pulses onto the tissue. The light gets absorbed and leads to a temperature and subsequent pressure rise. And by that, ultrasound waves are generated that we can use for image reconstruction. And with this, we can see up to several centimeters deep into the tissue. Now, by using light of several wavelengths, we can non-invasively see different endogenous absorbers within our body. For example, oxy and deoxyhemoglobin, and this allows us to non-invasively map the oxygenation state in blood in tissues. Another big advantage of photoacoustics is that we can visualize tissue at different scales. So we can look at whole patient tissues. We can look at cross sections of small animals, like it's shown in the second photo. We can also visualize vessels, but we can even go down to individual cells. And this is, of course, very useful in a context where the tissue structure and the microenvironment really contributes to the disease progression, as it is the case also in breast cancer. Now, one of the big first questions I wanted to answer in my research is whether we can exploit this novel, exciting imaging modality to better understand differences in oxygenation and vascularity in breast cancer, because this information might help us later on to better adapt treatment options and also to better understand the biology behind the cancer aggressiveness. So to do this, I used two different mouse models, MCF7, MDA, and B231. So MCF7 is an estrogen receptor positive, luminal A breast cancer model, and MDA and B231 is triple negative, so a very aggressive breast cancer. And the hypothesis was that in the more aggressive cancer, we can see higher hypoxia and also higher hypoxia dynamics over time. And we wanted to see whether photoacoustics is able to map this and whether we can then use this information to better understand the biology. So first I did a baseline characterization of this. So I looked at so using immunohistochemistry, I could prove that in the more aggressive cancer cell line, it's more hypoxic, the vessels are less mature, so less well developed, and we can also see a higher vessel density. And this is very common in more aggressive and more angiogenetic cancer models. This, I could also confirm this on a genetic level, so using RNA sequencing, genes that are associated with hypoxia and angiogenesis are more upregulated in the more aggressive MDA model compared to the more mature MCF7 model. Now, photoacoustics, which helps us in this case to look at the oxygenation, but also later I will talk a bit about the vessel structure, could really help us to non-invasively see in real time the development and oxygenation along tumor growth. And what we can see here is that in the MDA model, so in both models with increasing tumor growth, we see a decrease in oxygenation, so the tumor gets more hypoxic, but this was more pronounced in the more aggressive MDA model compared to the more mature MCF7 model. And the heterogeneity of the oxygen distribution was also more, more pronounced in the more aggressive MDA model compared to the more mature MCF7 model, which was an overall better oxygenated and more, and overall the oxygenation was better distributed within the tumor. So we also then looked, as mentioned in the beginning, at the variation of the oxygenation over time, which refers to the cycling hypoxia, which I introduced in the beginning. And here we could indeed see that in the more aggressive MDA model, the oxygenation varied much more intensely over time. And we looked a bit more in depth in this, so we could see that the fraction within the tumor which exhibit the cycling behavior was more pronounced in the more aggressive MDA model. And when we injected a contrast agent into the tumors, which is here called ICG, we could also see that this contrast agent better accumulated in the more mature MCF7 model, which really suggests that this model is better perfused, so the vessels are better functioning in this model. And we also performed a frequency analysis of the time series data, where we could see that certain frequencies in the oxygenation occur, which also align with what has been reported in the literature. And this really suggests that photoacoustics is sensitive enough to look at these oxygenation dynamics in real time and can really help us to better understand and really characterize this behavior. Now, I was also really interested in how does this connect to the vessels and the vessel structure? Because vessels are, of course, the main carrier of oxygenation within tissues. And what you can appreciate from these images, so these are photoacoustic mesoscopy images, that in the MCF7, in the more mature model, we can already see, just by looking at these pictures, that the vessels are better developed and more mature in the more mature MCF7 model compared to the aggressive models, where we see a lot of small vessels and also a very high vessel density, which really pinpoints to a more angiogenetic phenotype. So usually this says that these vessels are less functional and less well developed. Now, of course, we can look at this, and it's very important to just not do this evaluation subjectively, but we really obviously want to quantify this. And to do this, we developed a machine learning-based algorithm which really helped us to segment and skeletonize these data, and so we had like a 3D vascular network, and with this we could really then do more advanced analysis to really characterize these vascular networks in more detail. And here we could also confirm what we have seen in the immunohistochemistry data before, that in the more aggressive MDA model we could see a higher number of vessels, more connected components, a higher looping structure, and a sum of angles metrics, which really shows that the more aggressive MDA model has like a more chaotic vascular phenotype. Now, something which I'm currently also working on is we have, of course, all these RNA sequencing in vivo data for example, for the cycling hypoxia data. And now I'm looking in vitro, so that just means in cells, where I expose the cells to different oxygen conditions, and then really try to identify genes that are related to this higher cancer aggressiveness, which we can see, or which might be caused by these variations in oxygenation. Now, photoacoustics is something where several people around this world are currently working on. It has, as mentioned in the beginning, very high potential for early breast cancer detection. But how can we, when we develop such a new technology, how can we actually successfully transfer this to the clinic so that patients really benefit from this? And one key thing this is really to standardize different devices, and also to enable intra and inter-system comparison, and to really move this forward. I'm currently co-chairing a big consortium which has now, in the beginning obviously it was very small, but now has like over 170 international members, which not only come from academia but also from industry and the government. And just to highlight a few of the achievements which we've already got on the path to getting this exciting technology close to the clinics. So with a colleague of mine, I established a standardized data format, which really allows us to enable the comparison of data which have been acquired with different devices. We also achieved the integration of photoacoustic imaging data into the widely used DICOM format, which is the current standard which is the current standard to retrieve, store, and submit medical imaging data. We also performed a big strategic road mapping events with all global groups which are working on this technology at the moment to really highlight the big translational barriers at the moment and how we can overcome these in the next 10 years. And then I've been also heavily involved in the development of a standardized test objects because this is really, really importantly needed at the moment to allow intra and inter-system comparison of different devices. And for this, I'm also currently running a big multi-center study with lots of different research institutions across the world to really push this technology further to the clinic. Just to summarize quickly, so I hope I could convince you that photoacoustics is a very new, exciting, promising technology for early breast cancer detection, and that it really enables non-invasive evaluation of differences of oxygenation and vascularity in breast cancer, but that we really need international collaboration and standardization to bring this new technology to the clinics. And just to outline also the next steps, so at the moment I'm more investigating the genetic impact of hypoxia dynamics to identify new drivers of cancer aggressiveness, and also obviously continue the international standardization effort to accelerate the clinical translation of the technique. And with this, I would like to say thank you for everyone who has been involved in this, also in particular, of course, to this amazing charity, and I'm very, very grateful to be funded by this. And if you have any questions, then just let me know.
Thank you. Wow, that was amazing. I have actually a really naive question, and I think your slides towards the end showing that this is going international, etc., probably means that this isn't a problem. But I can't help wondering about, initially you mentioned that this the imaging technique causes a rise in heat, in temperature, and I just naively wondering whether there's any risks around that. Are you talking about,
So that is a good question. So we are completely under the safety limits here. So it is true that by pulsing a laser on tissue, this leads, of course, to temperature rise within the tissue, but this is completely so there's no damage to the tissue. So there's so the temperature rise is not as high as you might imagine it is. But very, very good question,
Good luck.
Thank you.
Thank you. Really nice talk. I may have missed this at the beginning, but this presumably uses contrast agents as well in order to visualize the specific structures. Okay, but I guess my question remains then, you've got one thing is about the implementation of the technology within the hospital setting. The other then is the translation of these contrast agents that you might use on top. So I don't know what you're thinking about that aspect of it.
So that is actually a very good question. So basically, the good thing or the great thing about this technique is actually that it doesn't have to use contrast agents. So basically, we can see, I could potentially go back to this graph. So we use essentially light of different wavelength and different molecules within our body. I'm just going back. Sorry. So here we are. So essentially, different molecules in our body, for example, melanin, lipids, collagen, water, have different optical absorption behavior. And by using light of different wavelengths, we can really pinpoint, for example, to certain absorption peaks of certain molecules. So what that means is that we don't need to use contrast agents. So we can, for example, if we use a wavelength which is more like, let's say, 500, we can look at like deoxy and oxyhemoglobin. But if we go higher wavelength, we can, for example, look more at collagen and lipids and water. So by doing multispectral unmixing, we can look at all these molecules without any contrast agents, so which is a huge advantage of this technique. Now, we can also use contrast agents on top if we want to, for example, look at specific molecules which might not have a very optical big absorption peak. And of course, this would then make everything much more complicated. I mean, if you, for example, look at like fluorescence-guided surgery, like just getting a molecule approved to do this is like, it's a whole other issue and makes everything much more complicated. But I think that's the huge big advantage of photoacoustics, that we are not tied to any contrast agent. So it just works by these optical differences which are intrinsically there. Sorry.
Brilliant, thank you, Dr. Hacker. So I'd like to introduce our next speaker from Bart's Cancer Institute, Dr. Oliver Pierce.
Thanks, Mark. Yeah, my name's Oliver Pierce. I'm from Bart's Cancer Institute, which is based pretty central London. We're very near to the Barbican Centre and St Paul's, so right in the concrete jungle. But actually, we've got a lovely grassy quad for our surroundings, very similar to Oriel College. So my lab focuses on the extracellular matrix, or the tissue composition and structure, and how that affects the immune infiltrate. So a bit like Lena's talk, we're more focused on everything other than the tumour cells. We tend to look at the other cell types that are present within the tissue. So I want to start with the clinical problem. So we're very interested in these reasonably new tumour immune phenotypes that have been described as desert, inflamed excluded, and inflamed. These describe the spatial arrangement of cells within the tumour microenvironment. And they're very important clinically because they describe the response to treatment, with what's called inflamed tumours being most likely to have a good response to therapy, particularly the immunotherapies, but potentially also the chemotherapies as well. So these inflamed tumours are characterised by having a very high infiltrate of immune cells that are capable of recognising tumour cells and eliminating them. But in the course of a cancer development, they get suppressed, so they get switched off. So something like an immunotherapy can come in, reactivate those immune cells and kill the tumour. Now, the inflamed excluded actually under the microscope looks very, very similar, and it makes up the largest group of cancers. It's the most common type of phenotype found across many different solid cancers. So it's got a very similar type of immune infiltrate, but if you look at the location of those immune cells, they're all restricted within the stromal region. They're not able to contact tumour. So what that means is that when you come in with an immunotherapy treatment, those cells get reactivated, but they're just never able to get close enough to the tumour to eliminate it. So in our lab, we think that the reason for this is the composition of the tissue, something called the extracellular matrix. And so what we want to do is develop ways of identifying what are the components of this immunological barrier, in a way to push these excluded tumours to being more inflamed and therefore therapy responsive. Here's an example of what this extracellular matrix looks like. This is a Masson's trichrome stain through a section of breast cancer. And what you can see here is, if I can use the pointer, yeah. You can see in purple these large solid clusters here. These are the invasive tumour cells. You can see there's lots of individual cells staining purple here. Those are those immune cells as well as other stromal cells that are present within the tissue. But what I want to draw your attention to is all of this blue staining here. This is the extracellular matrix. Of course, it's common to all of our tissues, and it gives our tissues the rigidity and the mechanical properties. But in a tumor, they become very fibrotic, and often this remodeling of the tissue makes up the majority of the tumors. In some cases, 80% of it by volume is actually extracellular matrix. So it's a big problem. Here's a close-up view of that using an electron microscope. So you can see that this ECM forms fibers, which are very tightly packed. So you can imagine as cells are interacting within this environment, their location is being controlled by the type of fiber being presented, but also their activity as well. This is coming back to the tumor immune phenotypes that I mentioned in the first slide. So again, this is sections through breast cancer, and then we've stained for a type of immune cell called a T cell in pink here. So these are cells capable of killing tumor cells. So in an inflamed tumor, there's plenty of contact with the tumor cells. So if you came in with a therapeutic here, you would expect a good response, that the tumor would probably mostly just dissolve away. But in the excluded, the immune cells are fixed or stuck within this stromal region. So what are the differences here between these tissues, between an inflamed and excluded? So to study this, we have three arms to the work that we're doing in the lab. So we have a target identification. We then test those targets in preclinical models, and then finally we have a therapeutics arm where we're developing tissue-focused therapeutics. So starting with the target identification, we had to develop a new pipeline for analyzing tissues, and that's because within the extracellular space, the type of structures that are present are quite different to what you would find intracellular within a cell. And so what we do is we combine structural and compositional data together with quite specific cell information or cell phenotype data. And what that gives us is graphs that look like this, where you can pick out individual structures and how they're associating with a particular cell phenotype. And from there, that allows us to look at associations which we can predict particular molecules that may have a role in generating a particular type of phenotype in a cell, or in fact be part of the immunological barrier that I mentioned earlier. So far we've identified several targets that we're exploring, and Priyanka will talk about one of those in more detail in the next talk. So once you've identified a potential target, we've got to test it. And again, this is another issue with looking at tumor tissues, is that there's no real good models out there for looking at extracellular matrix. Most of the models are more focused on cells and cell interactions. So we built a decellularized tissue model that we made initially for ovarian cancer, and then also applied that to breast cancers as well, and we've also made it for several other cancers. So this model reproduces the features of a tissue. So it reproduces the architecture of a tissue, and therefore it also has the same effects on the cells. When you add cells back into it, it suppresses their activity, as we see in cancer. Just to give you a closer look at what this model looks like down a microscope. So in this case, we've taken decellularized breast tissue from patients in London, and then we've recellularized with reporter cells. So in green we have tumor cells. In pink is it's a cell-based therapeutic that we're testing, but it's a T cell, so it's a cell that's capable of killing tumors. And so in this model, we're able to look at where cells are locating. We can look at things like their velocity, how are they interacting with each other, and of course we can also look at the therapeutic efficacy as well. So you can also pick apart things like, how do cells talk to each other? Can you use drugs to inhibit that cell crosstalk? So for therapy design, we teamed up with a therapeutics company called Neo Therapeutics. So they have a bacterial system for delivering payloads within a tumor very specifically. And what we wanted to do was take some of the targets that we'd identified and deliver enzymes into the tumor environment in a very specific way so that we could modify the extracellular matrix or the tissue architecture specifically within the tumor. I just want to show you some examples of one of these that we're testing at the moment and just show you how the approach works. So this is again in our decellularized tissue model. In red here is the tumor cells that have been reintroduced into the model. They form these clusters just like you see within human tissue. And then the bacterial vector come into the tissue, they go throughout it, recolonize, and once they've done that, they then express their payload. And when they do that, they're able to modify the composition of the extracellular matrix in situ. So essentially we can tune that extracellular matrix. And here's an example of that. So the purple stain here is one of the targets that we're going after. This is the tissue architecture here in the normal tissue. And then afterwards, after treatment with the bacterial vector, you can see hardly any evidence of that vector being present. Any evidence of that ECM molecule being present. And then after that, we look at then what effect has that had on the immune infiltrate, and does it improve elimination of the tumor? And so here's an example of that. Again, back in the decellularized tissue model that we have. So tumor cells again are in green. Blue is a pattern for this ECM molecule that we've been looking at, and pink are showing a CD8 T cell, so a cell that's capable of eating or killing tumor cells. You can see it happening here. So in the no treatment, you can see there's very few T cells that are actually able to get into contact with the tumor, just like we see in the human tissue. So we describe these as being immune excluded. When you come in and make a modification, you can now see there's much better immune infiltrate, and in some cases we're seeing better killing as well. In general, we see, depending on the molecule that we're going after, we're seeing an increase of about 40 to 50% increase in killing when you make these modifications first to the ECM. On this graph on the left-hand side here is showing you a correlation between ECM target composition and the response rate to treatment. The blue squares are where we've come in and intervened with a treatment to make a modification. So you can see there is a correlation, but it's quite a varying correlation. It's not perfect. And that's because there's other things probably going on in this environment. So for example, there are some molecules that we found which look like they actually support and stimulate our host immune system to kill a tumor. So although our method at the moment is perhaps quite crude because we're going in and making these enzymatic modifications, this gives us some ideas for the future that we can probably tweak or modulate ECM as opposed to digesting it to actually improve the immune infiltrate, as well as eliminating some of those immunological barriers. Just to very quickly summarize then, so the extracellular matrix makes up a massive part of tumours, is often not really considered, but it has a big effect on the immune response, and it does this in two ways. So it can act like a barrier, and so shield cancer cells from treatment or an immune response. But it can also alter cell function. I haven't shown you that today, but it can have a direct effect on the tumor cells themselves, making them generate a more therapy-resistant phenotype. But it can also have a direct effect on the phenotype of immune cells that would normally be killing the tumor. It actually drives them into phenotypes which support tumor progression. The good news is that it's really targetable. At the moment, we're using these enzymes to make these digestions, but there are other ways you can modulate these types of molecules, which would perhaps be less aggressive. And we think that we can do it in quite a tumor-specific way because these molecules are presented in tumor tissues specifically, and you don't see so many of them in normal, healthy tissues. And currently, we're using it for sensitizing tumors to what we'd call biological therapies. So this would be cell-based therapies, but also antibody-based therapeutics as well. But potentially it could be useful for more traditional chemotherapies. And finally, just to thank the people that have done the work. So we're quite a small team at Barts, but we benefit greatly from collaboration. So we try and be a very collaborative lab because we think that way we can get to answer the questions we're interested in quicker. And we are very thankful to Against Breast Cancer as well. The lab started with research with support from Against Breast Cancer, and it really allowed us to build that foundational data, which has allowed us to go on and now start to develop therapeutics. So it really, wouldn't have happened without that initial support from Against Breast Cancer. Happy to take questions. Thank you.
Hi, Albert. A great presentation. I'm just wondering, further down the pipeline, if you're using it as a sensitizer, is there potential that you're going to have some off-target effects on immune-privileged sites in the body by modulating the ECM? So I'm thinking more blood-brain barrier. You've got a more immune-privileged brain. It could cause sensitization of those off-target areas. Is that something you've considered, or maybe I'm just a bit ignorant and it's...
No, it's a good question. It's something we worry about all the time. I mean, the modifications we're making are quite small, so our hope is that we're not going to have these off-target effects, but until we've tested it, we won't know for sure. Yeah.
Thank you so much, Oliver. If there's any more questions, of course, there will be time in the breaks. So without further ado, invite our next speaker. It's Dr. Priyanka Hirani.
Hi, so I'm going to talk about my PhD project, which was funded by Against Breast Cancer and also Barge Charity, which was investigating the role of Verscan in immune exclusion in triple-negative breast cancer. So most people here probably know about this, but breast cancer has multiple subtypes, and our focus was triple-negative breast cancer. It accounts for around 15% of all breast cancers, and it has the worst prognosis of them all. So because of the lack of the HER2, ER, and progesterone receptors, these patients can't really have much targeted therapy and are limited to surgery with chemo or radiotherapy. However, one thing that is interesting about triple-negative breast cancer is that the immunofiltration is much higher compared to other breast cancers. So this led to the thought of, well, immunotherapy should work then. However, when you look at the trial results, they're actually quite poor, and only a quarter of patients actually benefit from immunotherapy. So when it comes to immune cells in the tumor microenvironment, it's really important as to the amount of them and also where they are. So Oliver touched on this before, but there are 3 different phenotypes. So the desert, the inflamed, where there's a high level, and the desert, where there's a low level, and also the excluded. And the main difference with the excluded compared to inflamed is where the immune cells are. So in excluded, the immune cells are kind of stuck within the stromal area where the ECM is and can't really have contact with the tumor cells for immune cell killing to occur. And this leads to kind of a change in the immunotherapy response. So as you go to a more inflamed tumor, you get a better response to immunotherapy. So when it came to my project, I wanted to try and look at, okay, how can we look at what are the different immune phenotypes in these tissues, and can we identify a target from this? So the first job was to try and identify what is the tumor immune phenotype from these subset of tissues I had. So this involved me scanning through different triple-negative breast cancer tissues that I stained for different immune cells, and then looking at where these immune cells were present around this tumor area, and then counting these using a QPath, which is a computational module, and then using this, I was able to show how these different immune cells are spread across the tumor. So looking at CD8 and CD68, which are tumor-killing immune cells, and how they are spread across where the tumor cells are towards the stroma, where you can see this extracellular matrix. And so initially, the first thing I wanted to do was identify which one of these are the desert tumors, which one of these have really low levels of immune cells. And from that, I could leave out the rest of the tumors and try and compare which ones are excluded and inflamed. So from this, I identified that around a quarter of the patients I had were actually inflamed for CD8, so T cells, while around a half were actually excluded, which is quite interesting because only a quarter of patients actually respond to immunotherapy. So this was quite representative. So the next stage was actually looking at, well, how do these immune phenotypes vary in tissue? So we can see that different patients have different phenotypes, but it's really interesting to notice that actually these phenotypes vary within one tissue. So one patient might not just be inflamed completely. They will have areas which are actually excluded and also areas which are desert, which can also lead to disease remnants after treatment as well. So it's something that has to be thought about when giving therapy as well. So the next stage was, okay, so we know the ECM might be having a role in this, so can we identify ECM targets? So various studies have shown that ECM can have a role in trapping immune cells, trapping drugs, but also the levels of expression of these different ECM genes have been shown to be associated with immunotherapy response. So can we target this extracellular matrix, and these proteins are present in this matrix? So a previous study in the lab showed that there was a signature of 22 molecules which were associated with immunosuppression. And within these, there were 5 that were upregulated at both the gene level and the protein level of these molecules. So my first job was to look at where are these expressed, is there some kind of correlation with their expression? And I was quite interested in 2 of these proteins, which was Versacan and cathepsin B. So I stained for these proteins in tissues, and I looked at which cells were expressed in these at gene level and compared this to immune cells. And what was quite interesting was I noticed that where there was a high level of Versacan expression around the tumor cells, so the epithelium, which are the tumor cells, those T cells seemed to be excluded around the stroma. So they weren't actually entering the tumor area. So this led to a hypothesis that is Versacan expression associated with immune cell infiltration, and could we target this to improve tumor immunity? So one of the things interesting about Versacan is it's found in different shapes and sizes. So it has different sizes depending on how big it is, and it can also have these glycan structures attached to it, which are chondroitin sulfates. And there are multiple cells which can actually express this protein. So there are tumor cells, there are fibroblasts which are present in the stroma, and also immune cells have also been found to be present to express this in metastatic sites. So I found that the immune cells were excluded in some tumors, and that Versacan might be associated with. So how does this link to each other? So when I looked at the levels of Versacan in these different phenotypes, there was actually no difference whatsoever. But when you look at where the Versacan is expressed, that's where you start to see the difference. So it's about understanding that it's not just the amount of protein, but where this protein is expressed is really important. And when you look at the spread of this Versacan in the different tumors, you can see that in tumors which are excluded, there's a equal level across it, where the inflamed tumors just have Versacan in the stroma. So again, it's this difference where we see this correlation where levels of Versacan in a certain area are associated with immune exclusion towards the tumor, which can affect tumor cell killing later on. So this is just kind of like an image kind of summary of this, where you can see that in excluded tumors, you see these immune cells in the pink are kind of stuck in this stromal area, and you get this Versacan, which is shown in brown, which is present within this stromal area, and the epithelial area quite highly on. What's also interesting is the cells are expressing it can also vary within these different tumors. So within excluded tumors, you have cells which are having close contact with these tumor cells, so they're kind of talking more to the tumor cells, while in the inflamed tissues, they're kind of spread quite far away from the tumor cells. So then the next part of our question was, well, we know Versacan's there, we know it's having some effect, how can we target this? And targeting is really important to have a very specific target for tumors to make sure that we don't have any background or any unwanted response in patients. So one thing we looked at was chondroitin sulfate. So these are glycan chains, so sugar chains present on Versacan. And what's really interesting about these sugar chains is they're present as disaccharides, so 2 different sugars together, but they have an extra level of complexity in the sense that they have different levels of sulfation within these disaccharides. So there are 6 different kind of variations of chondroitin sulfate, and the levels of these variations can have an effect on their roles. So in a collaboration I did with Dr. Kim Allange in Seattle, I was able to go there and try and measure the levels of these different chondroitin sulfate isomers in these tissues I had. So I wanted to see, is there a difference between the inflamed tissues and excluded tissues? In which isomers were these different and where were these different? So what I noticed was that actually when I compared the levels of the isomers in excluded tissues compared to inflamed tissues, there was a difference in the A and C isomers. And when you look at the ratio of these A and C isomers, that's where it's even more interesting, where you see that in inflamed tissues, you see a difference within the stroma and epithelium, while in excluded tissues, it's low, completely low in both areas. And that comes really important when we come to even some of our functional assays where I looked at Versacam from 2 different cell lines. How does if I remove chondroitin sulfate, does that have a big difference? And it does have a big difference, but only when this A and this AC ratio is also low again, which links back to what we saw in the tissues. So kind of the summary of what my PhD and what we found was that actually what's really interesting is that we see this difference in levels of Versacam within excluded tissues and inflamed tissues, but we also see this really interesting difference within the chondroitin sulfate levels. And that potentially, if we can target these chondroitin sulfate levels, we might be able to improve the gradient of immune cell movement into the tumor and then help this tumor cell killing actually occur. And with that, I would like to thank the funding for my PhD, so Bart's Charity and Against Breast Cancer, and everyone who's involved in putting together this project and the paper that we've just published. So thank you.
Thank you. It's a really nice piece of work. So I guess where my thoughts were going as to the therapeutic implications and how you might be able to target this. So as I noticed from your slide, there's a difference in the degree of sulfation between these isomers. So is that a possibility for it to think about a therapeutic intervention?
So when it comes to the actual targeting these chondroitin sulfates, there are actually enzymes we can target specific isomers of this. So in terms of therapies, what I was thinking of was something along the line of introducing these enzymes into a certain area, so maybe by an antibody or something, because I think one of the key things is we can't just remove these completely because that'll have a bigger effect. So it's about having these enzymes go into a specific area to cause what we need to happen to kind of bring across these gradients. So I think there are some enzymes available, but it's about how can we bring them to the areas that we want, and only those specific areas I think is really important when it comes to therapy.
But there are enzymes that catalyze both processes, so it might be possible to develop small molecule inhibitors. So think about the opposite approach. Right? Rather than having to introduce the specific enzyme to promote one direction, it's a specific inhibitor to block the opposite.
So I'm Mark, the research manager against breast cancer. So just like to talk a bit about funding strategies and future directions. So as most of you all know, our sorry. Check I'm muted. Okay. Against Breast Cancer funds vital research, and you've heard some wonderful talks already today from our researchers at Barts, Southampton and Oxford. Just to point out, we've had recent funding projects at the University of Sheffield, which I'll talk briefly on later. So ABC funds research in the 3 pillars of research, as we call them. That's prevention and lifestyle factors, early detection, and obviously therapies, which you've heard plenty of about today. So just a few statistics here. They're also on the boards in the break room. Hopefully that's better. Okay. So since 2021, a few statistics here for University of Southampton that Against Breast Cancer funding has funded 2 major research programs. That's ABD's Discover and therapeutic antibodies, which you've heard some of and we'll hear more later. Below that covers many research projects, 8 academic staff, as well as a number of published papers, presentations at cancer research conferences, and 4 PhD students funded in that time, which is fantastic. Of course, at Oriel, we found 2 research projects, senior and junior research fellows, which you've heard from today, Dr. Simon Lord and Selina Hacker, and clinical trials. Also fantastic that they're in collaboration between Oxford and Southampton, showing the great synergies that can be made across our funded institutions. And you've heard from Dr. Oliver Pearce and Dr. Priyanka Harani from Barts today. Just one thing to point out, in the last few years, there's been 10 additional research publications that have knowledge against breast cancer and the Diet Comp Life Biobank. So it's a great resource to the wider research community. Furthermore, the Breast Cancer Association Consortium, which publishes studies on the links of certain genes to breast cancer, has also acknowledged ABC in now at least 24 different publications. So, ABC has funded research, as you've heard, since 1993, and because we funded, this is a bit dry, this topic, but it's important, as the wonderful funds and efforts that people go to raise money, if you fund medical research, we have to be a member of the Association of Medical Research Charities, the AMRC. Now, they offer great advice and good best practice guides to funding medical research. There's a number of requirements for membership. I won't go into all of them, but they're available on our website, or the AMRC website. I'll just touch on two. Number two is we have to publish research strategy. And number six is that research strategy and funding research through grants is peer expert reviewed to carefully make sure the funds are being used for the best research. So, to that end, Against Breast Cancer has a 10-year research roadmap. It's updated biannually, which was a task I had at the back end of last year. So I was thoroughly impressed as a scientist who's worked in cancer for a number of years to read this document and see the amazing research that it covers, of which you're hearing about today. Our research roadmap, for those that are interested, is not really interesting, but 62 pages, 29,000 words. I admit I did add quite a few of those. 422 scientific references. And basically the roadmap describes, across the three pillars of prevention, early detection, and therapy, the review of the ABC-funded research, as well as the state of the wider research field, other breakthroughs across the UK and the wider world of breast cancer research, and seeks to identify critical gaps and priorities for future research. We also look at what some of the bigger breast cancer charities are funding, which is useful because we don't want to duplicate efforts with some of the bigger organisations. So if we feel a certain area is well covered elsewhere, then we will put our resources in a different direction. So ABC funding 2024 and beyond, we'll obviously continue to fund our core and fellowship programs, which you've heard about today. And also later this year, we plan to put out a call for proposals, an invitation to bid for future funding. And I'll just on that topic talk about, I guess, Against Breast Cancer seed grants. So these are small grants, up to 50,000, though that's not a small sum, but it just goes to show the cost of high quality research. That is to fund small early projects that have the potential to be truly innovative and have a real future impact on preventing loss of life through metastatic breast cancer. So those are designed for early projects with a small time frame, up to 1 year, maybe a short standalone project, or to finish off or complement an existing study, to use the phrase that Bernadette coined, the harvest fund, rather than the seed fund. So we have an application process. I won't go into details here, but there's a lot more details on the website. But applications, if they're received, will be expert reviewed by the ABC Scientific Advisory Board, of which there are members here today. So it comprises 6 experts across cancer, breast cancer surgery, immunology, epidemiology, and drug discovery. So we have a really highly expert independent panel to review grant applications. Additional input comes from our research advocates, which bring a more sort of patient-centric approach to make sure that this research will be funding projects that will lead to a real impact for patients. And just a final word on seed grants. The key is in the seeding of a smaller project, a smaller idea that can grow into something much bigger. And two great examples are Dr. Oliver Pierce, who you've heard about today, but also a shout out to Dr. Lewis Quayle, who was due to speak today, but due to his first child literally arriving today, in due state, he was very keen to attend, but obviously has a good reason not to be here. He received some seed funding from ABC and successfully published on methods of how cancer cells remain dormant and escape initial treatment and then later can re-emerge to cause secondary disease. So his work is summarized on a poster in the break room. But yeah, just to say that Dr. Quayle is now, with ABC support, applying for a much larger, more ambitious grant that would fund a larger group with some really exciting ideas to find novel therapies for preventing secondary breast cancer. So there's just a snapshot of Lewis's work. So thank you so much all for attending again, and if there's any questions, please fire away, otherwise I'll move on to Grace. So yeah, obviously be around if anyone wants to ask questions later. So my pleasure to hand over to Grace from the University of Southampton.
Yes, so I'm second year PhD student with the team at the University of Southampton, and my project is looking at breast cancer metastasis, so the real reason that we're all here, looking at secondary breast cancer, with a particular focus on how obesity impacts this and can lead to it. So we've heard a lot of statistics today, but I just want to focus on those middle ones, that even though survival has improved dramatically for breast cancer patients the last couple of decades, there's still 11,500 deaths each year. And the majority of these can be attributed to the spread of cancer from its primary site to other parts of the body. And this is what's referred to as secondary breast cancer, metastatic breast cancer, or stage 4 breast cancer. So people have referred to it in different ways today. It's all the same thing. And this graph from Cancer Research UK shows this, shows the importance of this. So as we've heard, early diagnosis has a really good survival rate, really good prognosis. But as the stage at diagnosis goes up, and when you reach this stage 4, which is where the cancer has spread, it's incurable. So all the treatments focus on managing the disease, trying to prevent it from spreading further throughout the body, but it's no longer curable at this point. And breast cancer can spread to lots of different parts of the body. The most common sites are the brain, the lung, and the liver. And the most common, which we're interested in, is the bone. Bone is also frequently the first site of metastasis, so often patients will present with bone metastases before then going on to develop metastases elsewhere. We're particularly interested in why the bone is such an attractive site for metastasis, what about it makes it special, and in particular, we work at the Centre for Cancer Immunology, so we're particularly interested in how the immune system is involved in that and how it could potentially be used to treat it or prevent it. So cancer spreads through a process called metastasis, and this involves the primary tumour, which will adapt, it become more aggressive, more invasive, and this will enable it to enter the circulation. So this can be either the bloodstream or the lymphatic system, and this will enable it to reach all the different parts of the body. and then it will reach a secondary organ like the lung or the bone, and then it will, what we call extravasate, so it will leave the circulation. And here it can either become dormant, like Mark mentioned, or it can immediately grow to form metastases. So as you can probably imagine, studying metastasis is quite difficult. It's a whole body-wide process. It involves lots of different cells, lots of different organ systems, and so it's currently not possible to do accurately in a dish. So we do use animal models to do this, and what my project is really focused on is trying to develop a model of bone metastasis. So to study metastasis, if you think about patients, not every patient will go on to develop secondary tumours, and it's the same with mice. If you give mice a primary tumour, you can't really reproducibly generate metastases, and you can't necessarily control where they go. And so to kind of overcome this issue, we administer cells at this point. So rather than giving a primary tumour, we put cells directly into the circulation, and this bypasses that initial step, which is often quite lengthy and quite, uncontrollable. And the benefit of this is that depending on where the cells enter the circulation determines where the organ that the cells will end up at. So if you think about your body, you've got your veins and your arteries, and the veins will carry blood back to the heart, where it then goes to the lungs, picks up fresh oxygen, and then the heart will take it back to the rest of the body through the arteries. So what we do is to generate lung metastasis, we will inject into the vein, primarily the tail vein, and then as the blood goes back to the heart and to the lungs, it will carry those cells, and we reproducibly generate lung metastases. So what we're trying to do, and this is new to Southampton, is develop this bone metastasis model, which involves administering the cells directly into the left side of the heart. So it's very specific, quite difficult, but this means that the cells will enter the systemic circulation, so they'll go around the body, and this will lead to bone metastases. And we've been doing this with guidance from Professor Ingun Holland's group, who have also received Against Breast Cancer funding in the past. And they use this method routinely, so we've been bringing it to Southampton. In the meantime, we've been looking at another aspect of metastasis, which is called the pre-metastatic niche. This occurs when there is a primary tumour, and before the tumour starts to spread, this primary tumour communicates with potential sites of metastasis and starts to change them and make them more favourable, more hospitable for when the cancer cells eventually arrive there. And this is something that we've been doing, again, in mouse models, and we're trying to understand how early this happens and how early it's established. But what we've seen, with a particular focus on the immune cells present, is that there is consistently an increase in a type of immune cell called a neutrophil. And we see this in the bone and in the lung. And this is coupled with a consistent decrease in another type of immune cell called a monocyte. So our next steps are to try and understand what these cells are doing and whether neutrophils could potentially be a target, either in disrupting this pre-metastatic niche or whether they stick around during the whole metastatic process, and whether we could target them throughout secondary breast cancer as well. And then just to finish, I just want to highlight this fourth statistic, which is that nearly a quarter of breast cancer cases are deemed to be preventable. And our lab in particular, aligning with ABC's focus, are interested on the impact of obesity in this. So obesity officially increases the risk of breast cancer in postmenopausal women, and about 8% of breast cancer cases are believed to be caused by being overweight or obese. So that might not seem like a very large number, but obesity also increases the risk of treatments not working, which is something that Charlie's going to speak about next, and it also increases the risk of cancer spreading and metastasizing. So to study obesity, we again use mouse models, and we feed mice either their normal diet, which is 10% fat, or a high-fat diet, which is 60% fat. And as you can see, this is the weight of the mice. Mice on a normal diet will gain weight very, very slowly and up to about 20 grams, where they plateau. But if you feed mice a high-fat diet, they just continually increase in weight and reach almost double the weight of a normal diet mouse. And they are visually different. They are visually a bit bigger. And we've been using these models previously in collaboration with Ingen again to look at how obesity is affecting the bone just outside of breast cancer. So to look at the bone, you can use CT scans, just like in humans, X-rays. So this is a CT scan of a mouse femur. So that's the upper leg, upper part of the leg. So this up here is the knee joint, and this is the ball that goes into the hip socket. And so with Ingen, we used micro-CT to look at the types of bone present within these long bones on mice fed either a control diet or a high-fat diet for different lengths of time. And what we see is that there is a difference. So in mice fed a high-fat diet, there's an increase in a type of bone called cortical bone. This is reflects what is seen in patients. So obese patients have been shown to have more cortical bone as well. So this just kind of is very sort of premature, but it highlights that obesity is affecting the bone even before you enter the sort of cancer environment. So my project is looking at combining these high-fat diet models with these metastatic models that we're in the process of developing to try and understand how obesity is promoting metastasis, how it's involved, and hopefully identify ways that it could be treated to either prevent it or treat it. Yeah, so just to end, it's all a bit off-center, but the main thank you is to all of you. Like, all of this work is funded by Against Breast Cancer. We couldn't do any of it without your support and your funding. But also there are a lot of people behind the scenes that have contributed to this, particularly at the Centre for Cancer Immunology, and then also our collaborators in Sheffield have been incredibly helpful with the metastatic bone model.
Thank you, and well done. So, being a second-year PhD student, so far, could you give us an insight into your conclusions you hope to achieve by the end of the third year?
So I think based on the stuff we've done so far, I mean, obviously the bone metastatic model we're still in the process of developing, so we're hoping that when that gets going, we might have some more answers. But the pre-metastatic niche stuff is suggesting that neutrophils are important. We don't really know why. It's been shown by other people with a focus in the lung that they're important. So our sort of next steps, and when we've got this model up and running, is to try and understand what roles they're having. But ultimately, it's kind of just making these models and combining them with the obese model and just trying to see what we see. Like, you know, look at the immune system, see what differences there are, see if these changes that are happening in the pre-metastatic niche, see if they're promoted by obesity, like without cancer, without a primary tumor. Primarily with the neutrophils, I think. I started this with we'll develop the bone model, and the neutrophils have just sort of kept coming up. So I think that's the road that we're sort of following at the moment.
Thank you.
Thanks, Grace. Two quick questions. I was wondering, with the obesity model, do you think the effects you're going to see are going to be caused from a hormonal perspective or actually from a mechanical perspective from the weight gain?
Good question. So particularly in the bone, so in obesity, you get an expansion of your adipose tissue, which produces aromatase, which is an enzyme that produces estrogen, basically. And that's why it increases the risk in postmenopausal women, because you have that drop in natural estrogen and the adipose tissue becomes the main source. So it could definitely be a hormonal thing, particularly with the bone, because estrogen is involved in natural bone, like homeostasis as well. The mechanical side of things, it's a good question. So the cortical bone is increased because of the increased load. So it could be that is also having an effect. Potentially whether the bones are weakened, I guess, by that load, and then whether that's making them more susceptible, not necessarily to cancer metastasizing there, but to when it gets there, if it weakens them and makes it a bit more of a easier environment to grow in, maybe. So yeah, it could be both. I think that's why it's so important for us to use the obese model, because it does have all of those different. It's not just adding in a hormone or adding in a particular type of like fatty acid or something. It is just trying to recapitulate the whole obese effect, which is why we plan to combine them. But yeah, they're both viable options, really. Yeah.
The other question was about the pre-metastatic niche. So there's different schools of thought on when it starts to occur. So some of the literature and more widely known is it's happening on later stages, but as it's more developed. But there's other literature indicating that it's happening really early on in the tumour's genesis. Is that something you're going to try and acknowledge or augment in the?
Yeah. So you're right. There's different. I mean, even with circulating tumour cells, people have shown that it happens very early on. Often, you can't. The problem with secondary breast cancer is you can't detect it necessarily until the cancer has already started to grow, and so a lot of the looking at the pre-metastatic niche and the circulating tumour cells does depend on how early it establishes. We're doing an experiment soon to try and look at exactly what you just said, how early that forms. We're currently doing it at a specific tumour size, which is obviously it's not very representative of patients, but in terms of the mice tumours, it's quite late. So yeah, we're going to sort of earlier stages to see whether it grows over time or whether it does just sort of appear almost immediately, basically. So yeah, it's something we're looking at.
Thank you, Grace. That's a fabulous talk. So next up, Dr. Charlie Burtz.
Thank you. Thank you very much for Against Breast Cancer for organising this meeting. It's fantastic, and thank you for inviting us along. Thanks for all the fundraising, everyone. Like everyone said, without this, we wouldn't be doing this work. So my name's Dr. Charlie Burtz. I'm Against Breast Cancer funded lecturer down at Southampton University. So I'm going to be talking about some of our work investigating the effect of diet and lifestyle on breast cancer development and therapy. So really to carry on from Grace's talk, I'm going to tell you about some of the research we've done as part of the antibody program, which Max introduced earlier, that looks at the link between obesity, breast cancer, and how these patients respond to antibody therapy. So we've got a nice picture of an antibody here, which, again, Max introduced. And antibody therapy has been proven to be a really useful and very good therapeutic strategy in treating cancer. However, it doesn't always work all the time, and it doesn't work in every single patient. And so we really want to try and understand that. So in order to look at that, we have to think or understand more about where the tumour is growing, the environment that it grows in. And this is something called the tumour microenvironment. So when you think of a tumour, you might just think of it as a mass of proliferating cancer cells. But it's actually, the actual environment, the tumour itself, is a lot more complicated than this. So, of course, we've got our proliferating cancer cells, but again, these wouldn't be able to grow and survive by themselves. Okay, they need a support network in order to be able to do this. So as well as the cancer cells, we then need the support network. So we need blood vessels to give them oxygen and nutrients and remove waste. We need an extracellular matrix, which Oliver spoke about, for them to grow on and give them support, okay, which acts as the scaffold. We need support cells as well, so like these green cells up here, which are called fibroblasts, which actually make some of this scaffold, this extracellular matrix. And then within the tumour, we also have various different immune cells. Some of these immune cells can actually act to sort of promote the tumour growth, okay, they can help that tumour growth, while other immune cells are there to try and inhibit and get rid of that cancer. So as well as all these other So as well as all these other cells which make up the tumour, we also have to think about where that tumour is actually sitting in the body and where it's growing. Okay, so we have to think about things what we call host factors as well. So if we think about breast cancer, of course, the primary tumour is going to be sat within the breast, and the breast is made up of connective tissue, glandular tissue, and fatty tissue. And in obesity and overweight, this fatty tissue, this massive fatty tissue can be greatly increased. And as Grace spoke about, obesity has been linked with both breast cancer progression, metastasis, but also it can impact how a patient might respond to certain cancer therapies, including antibody therapy. So we need to consider what is surrounding this tumour as well. So in obesity, okay, you get this increased massive adipose tissue, and within the breast, this increased adipose tissue can start to recruit into it various inflammatory immune cells called macrophages. And so this is just a histology slice from a patient showing these macrophages that have come into that adipose tissue. Okay, we've stained these macrophages red, and they form what we call crown-like structures around these adipose cells. And the reason we call them crown-like structures is because when we look at them in these histology slides, they literally look like little crowns sat on these fat cells. So that's what we've got here. So once these come into the adipose tissue, these macrophages can then start secreting other inflammatory factors and really act to sustain this chronic inflammatory environment within the breast that can start promoting that onset of breast cancer and disease progression and also metastasis. And so this is a paper that we published on the crown-like structures, but how these crown-like structures are actually driving or affecting the cancer progression, how they might actually affect how a patient responds to therapy is largely unknown. So this is why we wanted to start to investigate this. And like I said, we've now published some of this work in this paper here. And so to start to investigate this, we had a cohort of breast cancer patients where we had 200 samples from them. They all had a particular subtype of breast cancer called HER2-positive breast cancer. And we looked in these patient samples and we looked for the presence of these crown-like structures in them. We looked at where these crown-like structures were and how many of them there were. And then we correlated them to various clinical aspects. So did their presence correlate with age, weight, or how those patients responded to Herceptin therapy? So just very quickly, a bit about HER2 breast cancer. So with HER2 positive breast cancer, these cancer cells overexpress a protein on their cell surface called HER2, and this is represented by these red bars in this picture here. And HER2 is a growth factor receptor, so when breast cancer cells overexpress this on their surface, this promotes their growth and survival. And so the main first-line therapy for HER2 breast cancer is this monoclonal antibody therapy called trastuzumab, or you might have also heard of it referred to as Herceptin. So on this antibody, the hands of the antibody, they recognize that HER2 on the cancer cell and they grab hold of it and they tag that cancer cell as being cancerous and needing to be removed. And then the Fc part of that antibody, which we can call an anchor down here, will then anchor that cancer cell to an immune cell, such as a macrophage, that can then remove that cancer cell from the system. And so this is just a short video, which hopefully will work, showing you this in action. So in the middle here, okay, we've got a macrophage cell, this big blobby thing, and then these smaller cells are a cancer cell that have been labeled with an antibody to tell that macrophage that it needs to get rid of it. Okay, so if we look at this cell here, this has got the antibodies coating it. The macrophage recognizes that as a cancer cell, so it can engulf it and remove it from the system, and then it just breaks it down within the macrophage. And again, if we look at this cell down at the bottom here, the macrophage will recognize it as being a cancer cell due to it being labeled with these antibodies, and therefore it can engulf it, eat it up, break it down, and remove that cancer cell from the system. So when we started looking at these patient samples, we found that when those crown-like structures were present, they tended to mostly occur within the border region between the tumour and the adipose tissue. So for example, in this image here, we've got the tumour here, we've got the adipose tissue here, and we're seeing a lot of these crown-like structures appearing in the border separating those two areas. And really significantly, when we looked at these crown-like structures, we saw that in patients that had a BMI over 25, so this is overweight and obese patients, we saw a significant increase in these number of border crown-like structures appearing. So when we then correlated this to how they responded to therapy, this graph shows it here that in those patients that had multiple border crown-like structures, within their tumours, they basically had a significant time to reduction to getting metastatic disease, suggesting that they're not responding to that Herceptin therapy very well. If we compared that to those patients that had very few crown-like structures in their tumours, then these are actually responding to Herceptin really very well. So to try and understand that, we needed to think a bit more about the macrophage biology. So macrophages have got these Fc gamma receptors on their surface, which recognize that Fc region of an antibody. And we can think of these Fc receptors as having two different flavors. So they can either act as an on switch or they can act as an off switch. So the on switch will tell that macrophage to turn on that phagocytic function, engulf that cancer cell, while these off switches are kind of switching off that macrophage function. And so we wanted to see which switches were present on those crown-like structures in these patients, and whether which switches were present differed between healthy weight patients and patients with a high BMI. And what we found was that in patients with a high BMI, their crown-like structures had significantly more of this Fc gamma 2b, which is this off switch, on their cell surface. And again, we can see that in these images down here. So again, the macrophages themselves are stained in red, and then we stain the off switches with a brown dye. So in the healthy BMI patients, okay, we can just see the red macrophages with no brown staining. While in these high BMI patients, we're now seeing a lot of this brown staining, suggesting that their macrophages have got a lot of these off switches on their cell surface. And again, when we looked at how this correlated to how the patient was responding to Herceptin therapy, we saw that those patients that had multiple border crown-like structures, that had lots of these off switches on, basically had lost all benefit to Herceptin therapy, as if these patients hadn't received Herceptin therapy at all. While those that didn't have any of these off switches on actually again responded very well to Herceptin therapy. So what does all this mean? Well, this really suggests that this Fc gamma 2b, this off switch that's appearing on these border crown-like structures in these high BMI patients, could potentially act as a novel biomarker, allowing for the stratifications of patients to try and determine their effective treatment strategies. So as an example, what I mean by that is if a patient came into the clinic, we could take a biopsy, we could look for the presence of those border crown-like structures, we can have a look to see if they've got lots of off switches on them. And if they do, we'd predict that they may not respond very well to standard Herceptin therapy. And therefore, much earlier on in their treatment cycle, we could give them a far more intense anti-HER2 drugs so they could get that benefit a lot earlier on in their treatment. Leaves me to finish off just by saying, of course, thank you very much everyone here. We've got quite a big team at Southampton. Stephen Beers, who couldn't be here today, is very much part of the Against Breast Cancer team, along with Max. And I just wanted to highlight those members of my lab that are funded by Against Breast Cancer. So Annalise, who's our technician, who's here in the audience today. You've heard from Grace. And Lydia's another PhD student who actually has just finished, so she isn't here today as well. And of course, collaborators, Alistair and Simon Lord here in Oxford as well. And thank you very much for listening.
Any questions? Sorry if I missed that, Charlie. The models you used, was that the hormone responsive breast cancer type? Does this apply?
The models we're actually using in vivo are triple negative model.
Does the effective obesity, does it vary between the subtypes of breast cancer?
Yeah, there can be a bit of variability, but what we see is that in most breast cancer subtypes, it's having a sort of similar impact.
Right, and of course, it's the immune therapies that tend to work best in the triple negative breast cancer.
Yes, so antibody therapy in triple negative breast cancer tends to be checkpoint blockade inhibitors. And again, whether they work or not is really dependent on how immune that tumor is. So whether that tumor is immune hot or immune cold, so it's about how many immune cells are actually within that tumor.
Yeah, that's right. I should have said the immunotherapy type rather than the HER2 targeting of the antibodies, but yeah. Okay, if there's no more questions, we move on to Dr. Ben Nicholas.
Very much. I have the rather dubious honour of my title not matching at all what you're seeing in front of you, but I couldn't resist a bit of a play on words. So this talk is actually about personalised vaccines, anti-cancer vaccines, but the principal idea of personalised vaccines is that you have not a preventative vaccine, but one that comes after you have already developed a tumour. And the normal method of their development is that you take a sample of the tumour, you analyse its properties, and then you identify things that can then go into a vaccine that is then given to act as to prevent recurrence and metastatic spread. And so it fits nicely in with the ABC remit. And the idea of what I'm going to show you today is about how we train the immune system to better recognise the cancers that are present in the body, and therefore hope to then improve the design of personalised vaccines. So we kind of have to go back to basics a little bit in that our immune system is really in its comfort zone when it's fighting things that are very different from our own normal cells. So we will be talking about bacteria and viruses. We have two key arms of the immune system, which are the innate system here, in which all of the cells are not adapted to respond, but they just have their own basic characteristics. And then we have the adaptive immunity part, which is made up of the B cells and the T cells. And as you've been hearing so nicely from Charlie, the B cells may respond to infections by producing antibodies which can circulate around through the bloodstream, bind to problematic bugs and therefore neutralize them. However, one really effective evasion strategy for viruses and bacteria is to then reside inside cells within the protective confines of an outer membrane of the cell, which means that the antibodies can't get to them. And this is quite a good way of residing somewhere and not being seen by the immune system. And so through evolutionary development, we have T cells which are capable of recognizing cells that have an infection on their inside, and then can go to them and directly kill them by contacting them and killing them through direct mechanisms. So the kind of microorganisms that live inside cells, there's some bacteria, but all viruses are able to go into cells and reproduce inside of them. I guess the interesting part of the immune system here is that we have some innate cells here called the antigen-presenting cells, which include macrophages, which Charlie was just talking about, and another type called dendritic cells. And although these aren't part of the adaptive immune system, they're actually really key to it, because what they do is identify problematic infections, and they actually eat the bugs or the infected cells, and then they present them to the adaptive immune system to enable it to respond to infections. If we think about a normal infection, let's take a virus, for example, because it's quite a good system here. If we have a normal cell and it gets invaded by a virus, a really good strategy for something that's living inside cells and trying to escape the immune system is to proliferate hugely inside a healthy cell so that it can't be seen, and at the very last moment, burst the cell, pop out, and go on to infect lots and lots of other cells. So what they do is they live inside the cell and try and keep it as healthy for as long as possible, and then all of a sudden they'll burst the cell membrane, and then the bugs will be released and go on to infect things. And this is a process of cell death we call necrosis. However, our cells are adapted to try and identify infections inside of them, and if they can detect that there's a virus or a bug inside the cell, they will actually undergo a process called apoptosis, in which they do a controlled suicide, if you like. They package up their inner contents, including their DNA, into small digestible, what we call apoptotic bodies here. And on the outside of these little bits of cell are eat me signals that say, hey, I'm ready to be eaten, and I can be removed from the body that way. And the image that Charlie showed of the macrophage eating cells was them consuming cells that contain a signal that say, eat me. In that case, it was antibodies, but we'll talk about something else. Anyway, they get eaten by these antigen-presenting cells, which include macrophages and dendritic cells, which is what I was showing you in a previous slide. Now, when they're consumed, the infected cells or the bacteria or virus get consumed by the antigen-presenting cell, so this macrophage for the purposes today, and then they get chewed up into very small pieces, and then those small pieces of those pathogens get displayed on the outside of the antigen-presenting cell on two very key important molecules called MHC type 1 and MHC type 2. And there's been quite a lot of talk today about CD8 cells and how they're able to kill tumor cells. They also kill infected cells. And part of this system is that the antigen-presenting cells, by displaying these bits, can train T cells, the CD8 T cells, and support B cells to do their functions and to go on to kill pathogens. So this process is key. The antigen-presenting cells encourage B cells to make antibodies by supporting their proliferation and growth. But they also train T cells to recognize infected cells and expand the number of T cells that are then present. So I said that's the ideal situation. But in cancer cells, we have cells that are derived from normal cells. So they're much more difficult for the immune system to see, although they may look a little bit different from normal cells by eye. The immune system has to recognize the difference by feel. So the differences are not necessarily immediately obvious on a kind of molecular level. But what we do know is that cancer cells contain, on average, depending on the kind of cancer, about 400 mutations in their DNA that in some way change their properties. So these mutations actually make the cell cancerous, and they've occurred through various processes. But they can also change some of the intrinsic properties of the cell by changing the way that the proteins are that make them look a little bit foreign to the immune system. They're not massive changes. It's not like suddenly seeing a bacterial protein, for example, but they are very small changes to your normal cell proteins that make them look a little bit different to the immune system. And really, this is the difference that we want to enhance and train our immune system to recognize the tumor. Because if they're different enough, the T cells will attack them, and that will go on to be effective. So to go back to our schema here, if we have a cancer cell which gets eaten by an antigen-presenting cell, like a macrophage, and then gets chewed up, although most of the proteins inside that cancer cell will be just like the normal protein, so when they get presented on here, they won't do anything, the occasional protein, bit of protein, will be presented that contains a mutation that caused that cancer in the first place, and that little bit of mutation may be sufficient to stimulate the immune system to be active. Now, I guess one interesting part of this is that the antigen-presenting cells engulf the cancer cells, especially when they're undergoing this form of cell death called apoptosis, because they've got the eat me signals on the front of them. Okay? And so a significant, treatments with, for example, radio and chemotherapies can cause cancer cells to express those signals. That's one of the good side effects, I guess, of those kind of treatments. So they can train the T cells to recognize cancer cells, and thus to expand the number of T cells which can go on and fight the tumor. That's the idea. Now, we actually know that the body is capable of doing this all the time, because we know that there are T cells that can recognize a tumor within the body of people with cancer. However, we also know that that training is random, in a sense, or the rules by which it happens are not very well understood. And the response is not fully effective, because otherwise you wouldn't have a cancer develop in the first place. So in typical biological fashion, my approach has been to say, right, well, let's go back to principles and see if we can understand the rules by which these antigen-presenting cells present the bits of cancer and then train the immune system. Because if we can find them, we might be able to use those bits to do it ourselves and to make it more effective. Okay. So the plan is to induce cancer cells to go into this special kind of cell death, and then to get them eaten by the antigen-presenting cells, and then to see to maximize this process to get as much presented as possible, and then to see which bits of them are being. So the first part of that is, can I make them go into the special kind of cell death that we want? Well, I take a triple negative breast cancer cell line, and I treat it with a chemical that I know will cause them to go into apoptosis to make sure that I am doing things right, but I also zap them with UV light separately to see which one is more effective. The reason I want to use UV light is it's not a chemical, so it won't affect the cells after it's been ingested by the treatment. So you can see by this graph, hopefully I'm cutting straight to the chase because I'm getting short of time. So you can see that if I don't treat the cells, here I have healthy cells and here apoptotic. If I treat them with the chemical that I know will induce apoptosis, I vastly increase the number of apoptotic cells. If I zap them with UV light, I get that number up to 82%. A vast proportion of the cells are expressing the signals that say eat me. And that was the key part of this first bit of the work. So I can make them go into the right kind of cell death. The second part is, can I get them to be eaten as a consequence of that? Well, I can grow antigen-presenting cells in a dish if I treat them with chemicals, and I can stain them with a red coloration, much similar to what you've seen shown just previously or recently. Then I can do the same procedure with these triple-negative breast cancer cells here. I zap them with UV light to make most of them edible, which was the aim. Unfortunately, that's supposed to be green, but it kind of looks weirdly kind of brown for some reason. If I mix them together and I take a photograph, I can see that I have lots of red antigen-presenting cells, and they're interacting with the green cells, and they've all kind of gone a little bit bitty. And if you can look at the little, well, it's kind of small here, but these little red arrows are showing bits of red cells with little bits of green cell inside of them. And if I add an inhibitor of them taking up or engulfing those cells, you can see that the relationship between those two cell types is completely different. These are all not interacting at all. So I've stopped the cells from being eaten by adding this inhibitor. But if we look up close, you can see that in one of these, where the green is inside, you can see there's an apoptotic cell inside there being consumed and chewed up. And that's what we want to encourage. But we can't just look at it and rely on that data. So we can do something using something called flow cytometry, where we look directly at the cells and we can count them and the interaction between them. So this is just the antigen-presenting cells. This is the green apoptotic tumor cells here. If we mix them together, we create this population here, which is a mixture of the two. So that's red cells containing green cells. So we can quantify how many are inside. And you know I said I added that inhibitor. Well, this is what this looks like here. So with the inhibitor, this is shifted over because not so many are positive for both. So we know that we're able to stop the cells consuming the tumor cells. And if we can put that into numbers, we can see that when we mix the tumor cells and the antigen-presenting cells together, 78% of them have taken a meal. They've eaten the cancer cell, and that's exactly what we want. And we can inhibit that by adding an inhibitor and knock it right down to about 30%. So we know that what we're doing is right. We're encouraging the cells to be eaten, and we can see that and quantify it. Final part is, well, okay, but the aim is to get them to digest up the proteins and present them on the surface. Can we do that and measure it? Well, I had an initial panic, because when I look at the amount of MHC1, which, if you remember, is the thing that stimulates the CD8 cells, which are the ones that go on and kill the cancer, when I added the triple-negative breast cancer cells to the antigen-presenting cells, the amount of this stuff went down, which is not what we want. We want it to go up. So I then had to go back to the drawing board and find something, a chemical, which then basically acts like a digestive for the antigen-presenting cells and enables them to more speedily chew up the things on the inside and present them on the outside. And when I do that, I maximize that. So if you compare that with this, I've tripled the amount of that on the outside, which means that these cells, having consumed the cancer cells, should now be optimally able to stimulate CD8 T cells that can go on and kill cancer cells. Similarly, for the other one, this is the part of the immune system that acted as a helper and stimulated the B cells to make antibodies. Well, the antigen-presenting cells didn't have any of this on at all when I first fed them. But when I'm able to stimulate the cells with something to add as a digestive, I'm able to then get very big expression. This is a 200-fold increase in the amount of the bits of cancer cell that could be presented on the antigen-presenting. To summarize, it's possible, this is a model in a dish that simulates what happens when the macrophages around your tumor consume the cancer cells, and we're able to do this in a dish and to create optimal conditions to find that. Now, the important part is the next steps, which is the kind of work that I'm normally involved in, which is to identify what those are. And so the very next stages will be to have a look at exactly what those cells are showing to the immune system and characterize them And using that information, we can then more optimally work out what is happening in real life and use that to design vaccines more effectively. Thank you very much. Any questions?
Fantastic talk, thanks, Ben. Yeah, on the vaccine part, so this is really elegant, complex work that's leading towards vaccine targets. It's more of a comment, really, that people might be interested to hear your views. We sometimes get asked, well, COVID vaccine was made pretty quickly, and there's vaccines to things like HPV, but of course they're caused by completely foreign viruses in a fairly limited number. Of course, breast cancer is not caused by one thing, which is a challenge.
No, that's right. So I've been doing work in actual tumour samples for most of the last 7 years. And the complication is that, and what I didn't make clear was that this is in a dish, and so it's predictable because we have two predictable cell types, exactly what's going to happen. But in a person, the mutations that go to change the cells to make the cancer are individual to every single person. All the mutations in that cancer are completely unique to that person. And therefore, designing a vaccine has to be, by definition, personalized because you have to sample the tumor, work out what's different, and even that's not straightforward. You have to sequence the entire genome of the tumor to find out where the mutations lie, and then you have to use that to try and predict what effect that will have on the tumor cells themselves, and then go on to then design a vaccine personalized for that. And so the whole process is, at the moment, reasonably slow and not terribly predictable. It only has about a 5% prediction rate at the moment. So the whole aim of this work is to try and streamline that process and understand it better so that we can approach that in a more systematic way.
Okay, thank you. You just got me thinking with the last thing you said. So how much heterogeneity is there within an individual patient's breast tumour? And so is that going to complicate further the strategy?
Well, I mean, and that's actually why I've gone back to this. That's a really good question. How much heterogeneity? That we kind of, like Charlie said, you kind of imagine that a tumour is just a lump of cells all of the same type, but they're not. Actually, they're incredibly complex. They're made up of immune cells, fibroblasts, all types of other cells, all mixed together. And within that even, not all the mutations in that tumour are the same. Exactly. You have regions which contain different mutations. And so the approach that we've been taking, where we take a tumour, identify the mutations, and then design vaccines against them, well, of course, there's always the risk that we will be immunizing against some of those mutations, but not all. So it may not be fully effective. But the idea is that if we could identify as many of the mutations as possible and be more effective about which ones are likely to train the immune system most, then we would be better able to design vaccines, optimizing the bits that we know are going to be most effective, most effectively produced. Because actually the problem that we have is not that we can't see what they should be, but the problem is that the immune system selects which bits it shows, and nobody can predict that process. So we have to, it's a kind of, that's why the 5% rate, because you might find 100 things that you want to do, but you can't put them all in a vaccine. You have to prioritize which ones you think are going to be most effective. And at the moment, that's an open field. We don't know which one is best.
Right, if there are no further questions, then we come to our next break, refreshments, and we rejoin at 3 o'clock for our question and answer panel. Should be a great end to the day. So thanks to the speakers for this session. That was fantastic. Right, thanks everyone for coming back. Now, it's my great pleasure to introduce the question and answer panel, hosted ably by our own Richard Martin, events manager at ABC. So Richard has a selection of questions. There will be an opportunity for people from the floor and even online to ask questions, but we'll kick off with Richard, please.
Thank you, Mark. Hi, everyone. As Mark says, my name's Richard Martin. I'm the Senior Fundraising Manager Against Breast Cancer. Just want to start, first of all, by thanking not only the panel here, which I will thank in one moment, but everyone today who has joined us, both online and in person. Amazing to see so many people, and thank you so much to all the speakers today. It's been marvellous to hear about all the amazing work, and I'm sure everyone will agree, all the work that goes on in the fundraising space and all the work our supporters do. It's amazing to see what that achieves and what that helps you find researchers and professors to do, so thank you ever so much. Thank you also, as I say, to our wonderful panel who are joining us here today. It's fantastic to have such a great spread of people from different backgrounds. We've got medical professionals, those that work in the support of breast cancer patients, and even some with lived experience of breast cancer. So it's a really exciting group of people that you're going to hear from today. So what I'm going to do, without much further ado, is I'm going to get the panel to introduce themselves, and then we'll go through a little bit about how the format's going to work. So please take us away.
So my name's Simon Lord. I'm a clinician, medical oncologist. So I treat patients in the clinic with breast cancer. I'm based actually within the university here in Oxford, and I lead a clinical trials unit that specifically runs phase 1 trials of novel drugs. So we're essentially putting drugs into cancer patients for the very first time. But I have a lot of interests outside of that, and you saw some of that in my talk. So in particular, how patient metabolism can affect drug response.
Hi, good afternoon. I'm Dennis Raimundos. I'm one of the breast surgeons at the Churchill. I haven't been called exciting ever in my life, so thank you. I treat patients with breast cancer coming from the screening program or through the GPs. I see them, assess them, and offer them the treatment options, and then tend to refer them to Simon if required. And then we just talk about how we can reintroduce them to life after breast cancer, so before we sort of send patients over to oncology. And again, if they have problems in the future, then we look to adjust them, whether that's reconstruction, adjustment surgery, or anything else that may be required.
So I'm Vicky Harmer. I'm consultant nurse for breast at Imperial. So I head up the breast screening and the symptomatic services. I am there when people are diagnosed with breast cancer and work as their key worker. So walk alongside them throughout all of the treatment modalities along the trajectory. I do a nipple tattoo clinic and hopefully head up all the service improvements and write the patient information. The exciting thing about me is that I've been a trustee for ABC for probably about 20 years. And I've also helped with some scripts for medical storylines, so EastEnders, Coronation Street, a few films, things like that. So delighted to be here. I'm pleased to be called exciting.
Hi, I'm Dave. I'm one of those rare men who's actually had breast cancer, and so I'm the recipient of all the expertise to my right. So I had breast cancer in 2015. The only argument I ever had in my breast cancer surgeon was he wanted to take my right nipple away, and I've protested but eventually gave in. So as a result of coming into contact with Kerry to my left, Kerry was the founder of the Men's VMU. It's the only support group in the UK for men with breast cancer. Not a huge number of us, because there aren't a huge number of men suffering. So there's about 40 members of the group. We come together once a month. We do a lot of work in terms of trying to raise awareness of breast cancer in men. We work with a range of charities, including ABC. The opportunities the VMU, as we call it, has given me is I've been able to, or I now sit on the National Institute of Clinical Excellence Breast Cancer Committee, on a National Research Funding Committee, as a direct result of my experiences with breast cancer. So I was able to turn a negative into a...
Thank you. My name's Victoria. I quite like this title, Expert by Experience. Thank you for that. My PhD is in nothing to do with medicine. It's in business, so if you ask me about business, I can answer that. But I first met Against Breast Cancer in 2019. I had primary breast cancer in 2012, age 36. My son was only 1 year old. I'd been breastfeeding, quite a shock at that time. Kind of carried on, lived my life, and what I didn't know was that when I ran the London Marathon for Against Breast Cancer was that I actually had secondary breast cancer at that time. I've recently been promoted to a super supporter of Against Breast Cancer, so thank you for calling us exciting, and I am really excited, and today it's been a real pleasure to gain knowledge actually and expertise around the stuff that's actually happening to me, and I know some other people in the room as well, so thank you for that opportunity. Thank you.
Last one to kind of round off the panel. I'm Kerry Quincy. I'm a senior lecturer and researcher at De Montfort University in Leicester. I'm a psychologist. Health psychology is the area that I teach and research in, and my PhD research was looking at the psychological experiences of men living with and beyond breast cancer diagnosis. And born out of that, as an offshoot, lots of people have been speaking about their research today in terms of where next, which is always the important. One of the developments from my PhD research was co-founding the Men's VMU alongside Doug Harper, who, together with Dave, is moderator of the Men's VMU.
Thank you very much, everyone. So, without further ado, we have a couple of questions that have been handed in advance, so we have a couple to go through. Those of you in the room, Steph, as she has been so brilliantly all day, is able to come round and bring the mic round, so do have a think if you've got any questions to ask following the ones we have. And also, anyone joining us online, please feel free, and they will be passed through to me as well. To kick us off, the first question's for you, Simon. As you're in place perfectly to my left. What are some of the latest advancements in breast cancer research?
Well, I'm not going to focus on, I'm going to focus on one thing, perhaps. And I'm not going to focus on treatment. We actually talked a bit about it, not myself, but earlier, and that's early cancer detection, which is sort of, I guess, a pan-cancer comment. But I think this is going to, almost certainly is going to have a dramatic effect on early on cancer treatment ultimately, because we'll be picking up cancers much earlier, and specifically using blood sampling, whether that's with the sort of microRNA techniques that were mentioned, or epigenetic, so modifications of circulating genetic material. These tests are already being examined in the clinic, and I think there's a pretty good chance in the next decade that we will be starting to screen patients routinely, say with a yearly blood test, certainly if you're high risk, perhaps over the age of, I don't know, 50 or something. And that will have not just a big impact on some of the screening services that we already have in place, such as breast screening. That maybe breast screening will not be required in the future, or at least will only be used for very high risk women, and we'll move to these sorts of blood sampling strategies, which could be done within primary care. But we'll also potentially pick up other types of cancer as well. So I think, and as I say, that will then lead to maybe more cancers getting treated early. We might pick up a lot of breast cancers, for example, that actually maybe didn't need treatment. We probably treat a lot of breast cancers that fundamentally would have remained indolent for many years and perhaps not cause problems. So it could have a major impact on health services, but also potentially make cancer much less of a serious disease, at least in terms of, because if you're picking up early, you can treat early and you can stratify patients better potentially with some of these blood tests to determine how impactful that treatment has to be and de-escalate treatment essentially.
Thank you ever so much. This question follows on quite nicely. It's for you, Dr. Victoria Harmer. How effective are current screening programs and how might these be improved?
Screening, thank you. And yeah, lovely segue, thank you. So screening, for screening to work, people have to turn up. That's always a little bit of a sticky wicket, depending on the geography. London is lower uptake, and we were down to about 40%, 10% down on normal just during the post-COVID. Now, London, we're a different beast, I suppose, because we have the transient population. We also have people who go for mammograms privately, do their own screening, if you like. And then there's a lot of potential language barriers. We've also got cultural beliefs, so people don't turn up for screening, religious beliefs, fear of hospitals and mistrust of healthcare professionals and of screening, etc. So there's a lot that we can work with. We can try to make better. We can try to make the service better for people who do have an interaction exposure to it, in the sense of quality is better, and customer service courses and things, so that anything is pleasurable, and greet people. I did an MBA, and it was on how we can get better at screening, and also people's perceptions of these mobile units. But certainly, I think also we could extend opening hours and weekend to try to get people to attend. So that's one of the ways that we can make screening a bit better. We used to have the age extension. Now it's purely 50 to 70-year-olds, and then anyone who's over 70 can contact the hub, which I suggest they do if anyone knows anyone of that age group, and ask to be included also. And of course, we do pick up, I think, as Simon gave a little nod to, these cancers which may stay indolent, which may not become, these precancerous changes also, which may or may not become an invasive cancer. So there's a lot of discussion and controversy about screening, but if there's one message to get across, it's that screening is a really good thing to do, getting these early detected breast cancers, and then we can do something about it. And then, of course, we've got to dovetail our support and treatment to that person in a personalised way. We're hearing today all of the personalisation of the cancer itself, but also to the person who come to us with this potentially life-threatening disease. Yes.
Thank you very much. Our next question is for Dr. Kerry Quincy. How might we best support patients in managing the emotional and psychological aspects of a breast cancer diagnosis and treatment?
Thanks. So when I saw this question as one of the ones that we were sort of given previously to look at, I want to say I cheated a bit because I have access to a group of men who take part in the VMU, and I feel very strongly about speaking for people and that patients have their own voice and that their voice is heard. So what I'm about to say is sort of a bit of a summary of my thoughts, but actually reflects more and represents their thoughts and opinions on this. And Dave will vouch for the fact that I did send the question round for people to contribute their thoughts if they had any. And so I guess really, from my perspective, I think it really is time to move away from, and it's really encouraging to see today that we're really starting to do that, I think, as researchers anyway, move away from a one-size-fits-all model. Breast cancer is not just pre or post-menopausal that are affected by this illness. It affects an absolute array of people. It doesn't discriminate in ways. It affects men, it affects women, it affects people of different ages, different sexualities, ethnicities, and it really is vital that we recognise and respect people's individualities and their differences at the point at which they are diagnosed in order for them to respond to diagnosis and treatment accordingly. And so in terms of kind of how best we can support these individuals who are diagnosed with breast cancer, whatever stage that might be at, the kind of loud banging of the drum that kept coming through from the men was a real need for clear informational written information that is factual, that is appropriate to the people that it's being presented to. So don't give a man a leaflet about how to cope with menopause or how to wear their bra post-mastectomy. Give them information that they can refer to after and outside of that clinical appointment, because they won't remember it in the moment. It's unfair to expect their another that goes in with them to remember that in that moment as well, because they're just as broken by that news as the individual themselves, and probably thinking all manner of different things alongside them. So the information needs to be factual, it needs to be right, and it needs to have the right tone and be appropriate. It also needs to be, and I feel again very strongly about this, co-created and developed with patients themselves. Let's stop talking for and doing research on and start researching with and including the individuals who actually know more about this in many ways than we do. And I think that sounds so obvious and so easy to do, and I appreciate it's not that easy to do, but we can make strides towards that, so that what I think is really vital is that patients recognise and see themselves represented in the materials that they're reading. If you are, and forgive me, I will use men as an example because that's kind of my bread and butter in this sense. For a man to pick up a leaflet that is entirely written about women and how you deal with breast cancer as a woman affects them hugely psychologically. It's about creating safe spaces for patients to discuss things and to open up about their vulnerabilities. If they are afforded time and space, people will talk. I say this repeatedly, again, where men are concerned, there's this assumption that men don't want to talk about health. That's absolutely rubbish. It's just that they're not being given the right arena to do so. So they're the kinds of things that were coming through when I asked the patients themselves what they thought we could do to kind of best support them, really, in a shot, I guess, without hogging the panel questions too much.
Thank you very much. Our next question's for you, Dennis. For a patient who is told they require surgery, what choices may they have?
I want to go back and say one thing actually about the men, women, and representation. We're talking about men here not being represented in the leaflets, but actually I think the average woman many times is not represented, even in the women's leaflets. And that makes it even more difficult. If you think that you've made the leaflets for women, and even the women don't feel represented, then it makes it even more difficult. Which does actually bring to the surgery, because you give people all these booklets about these are your surgical options, your reconstructive options. People are overwhelmed, they're scared, they're afraid of dying. Like that's, even if your cancer is not bad enough, anywhere near bad enough, you're scared, and then you're given a lot of information to go through, and then you need to decide on surgery. And it's a very difficult time, I think. For the majority of the women, there is usually a choice between breast conservation and a mastectomy, so a lumpectomy or mastectomy. We call it breast conservation because there are lots of different fancy things that we like doing and make our head look even bigger, and we think we're amazing. But actually, we have moved on over the last 20 years to find ways to do breast conservation and to have, I think, excellent results for many patients. Patients are very scared. They don't know what the scars are going to look like. It is very difficult. But they have the option of breast conservation versus a mastectomy. And again, a mastectomy as a term is awful, scares people. And it can be a simple mastectomy, so a flat mastectomy as most, or it can be a skin-sparing or nipple-sparing mastectomy, depending on the patient's disease, depending on the patient's other risk factors. And if that's the case, you can have the option of a reconstruction, which could be either as an implant-based or as a tissue-based or a bit of a combination of both. Not all of these would be options for everyone. You can't have a tummy reconstruction if you don't have enough of a tummy. You can't have a tummy reconstruction if you are morbidly obese, because you are more likely to die from the surgery rather than potentially from any problems from the cancer. So you need to tailor it to the patient. There are certain patients that will not be given any choice. And when I speak to them, I think that's really, really difficult, because everyone needs to have a choice. But if you have, for example, a more aggressive cancer that maybe involves a lot of the skin of the breast, or there is inflammatory changes, what you need actually as a cancer patient is to get on with the treatment, finish your treatment. You can have the option of a delayed reconstruction afterwards. And when we don't offer the option of an immediate reconstruction, I think people are fully aware that this is not easy for the patient. This is not easy for us. Like, we like people to have a choice and choose whatever they think is right for them. And everyone is different. I've had 30-year-old patients choosing to have a simple mastectomy, flat mastectomy. They've never come back. I'm very happy. I've seen people that went flat and their colleagues made them feel guilty for not having a reconstruction, looking for psychological support from me for not having a reconstruction. It's your choice. And there are other women in their 80s and 90s, they've come to me as a second or third opinion. Can you do something to conserve my breast? Many people may have thought, well, you're 85, 87, the breasts have served their purpose and it's fine to have a mastectomy. Well, it isn't. It has to be fine for her. So you need to tailor it to the patient.
Thank you, Dennis. A question for Victoria Smith-Collins, as there are two of you. What aspects of breast cancer care and treatment do you believe could be improved?
Thank you. And can I just say that what the people on the panel are talking about is really relating to me very closely, because I have lived experience of this. And certainly when I was first diagnosed with primary breast cancer, having a support network, having support there is very, very important, because when the consultant gave me the options and I was feeling overwhelmed, and at that time I just want to survive. I mean, I have 3 children and the youngest was 1, and I just needed to survive. But it was actually the Macmillan nurse at that time that took me to the side and had created a safe space and had a conversation with me about, actually, you are young and in the future you might care about this. Because I was just kind of like, just get rid of it. I just need to get rid of it. That's all I need right now. But actually what I've learned over a period of time was those conversations were so helpful and significant, because I did care about it later on, and I did have a reconstruction with tissue because my stomach was okay. And actually I ended up, sorry to be a little bit controversial, but I ended up with a better pair of boobs than I had before I even started, actually. Sorry, but that's the reality. That was the reality. And a tattoo that started with a nipple reconstruction. But definitely I think the support, the one-to-one relationships are very important. The knowledge. After having a secondary breast cancer diagnosis in 2020 during COVID, I was frightened to ask those questions about, I was put on a treatment of immunotherapy, but like, what's next? What happens when that doesn't work anymore? And I was very frightened to ask those questions. And it took me nearly 3 years to actually ask the question for my oncologist, like, when this treatment doesn't work anymore, which it did stop working last year. And I'm now on a different treatment because I have some further spread to the liver. Actually, the oncologist said, no, there's a menu of different options available that I just completely wasn't aware of. So I think this kind of knowledge, the personalised treatment, creating safe spaces for support, I think coming out of COVID, from my conversations with other people going through cancer, it's sometimes been a bit disjointed in terms of where you get support or where you get communications from, and sometimes that folder full of information can be a bit overwhelming, but to find places where we can get that kind of tailored support and a network of support, I think is very important. And I think it's improving coming out of COVID, but still there's a little bit of work to be done in terms of having that one-to-one relationship with certain experts and support groups as well. Thank you.
Thank you. This one's for you, David. For someone diagnosed with male breast cancer, what unique difficulties might they experience compared to someone with female breast cancer or other cancer types?
The first thing I would say is that the treatment between male and female breast cancer is very, very similar. There's a couple of differences, but in that sense, and in fact, I would acknowledge that actually I would say it's harder for women because I had a mastectomy. Unless I'm swimming, you wouldn't know it. I lost my hair, but for a man, that's not so much of an issue. So in that sense, men are perhaps a bit luckier. The issues that we have are in terms of, we've touched on it already, is lack of information. Now, I had my cancer in 2015, and I was very lucky because I was treated privately because I had health insurance, but that meant I had access to a proper breast cancer nurse who was aware of male breast cancer, but she was the exception to the rule. Now, I was given a leaflet. So there was no folder of information. It was a leaflet. And when I then went out, went with my wife to actually find out more, and I turned to breast cancer charities. I wasn't aware of ABC then, but I went to Breast Cancer Now. There was absolutely nothing there to help or guide a man with breast cancer. And it was to be 4 years before I actually met another man who'd had breast cancer. Now, my career background is in policing. So another challenge for a man is, particularly in a highly masculine environment, to say to your colleagues, now I had actually retired by the time I had it, but I'm still working with the police service. Oh, I'm a man with breast cancer. Your anxiety levels are really high because you don't know what response you're going to get. Your instinct is that you're going to get a hard time. The reality is that the police service as a group kind of metaphorically put their arms around me, gave me an enormous hug, and 6 or 7 months later, as I came out of my cancer, I stood in front of 2,500 police officers dressed in a bright pink suit with no hair and told them all about the fact that men get breast cancer. Just after that, talking to that, a guy came and spoke to me and said, I've got a lump. And he actually, police officer, was diagnosed with breast cancer. So I like to kid myself that at least I may well have saved a life. But that's the problem. It's the lack of information. Now, we as men and men at the VMU, we recognise that there's only 300 or 450 of us. So our expectations have got to be reasonable. But it's simple things like my wife and I we did use the NHS on a couple of occasions, went to a breast cancer clinic together, and the lady behind the counter just spoke to my wife, said, who are you here to see? Now that is something that shouldn't happen, should be easy to train. The receptionists and staff in breast cancer clinics should be advised, look, it might be a man who comes in. Now the impact on that may not seem mean that much, but when you're on the receiving end of it, you've already got an awful lot to deal with. You're stressed and you're frightened and you're upset. So if the system doesn't recognise it properly, then there's a problem. So for me, the challenges were in that sense. Now, Kerry's and Doug's creation of the VMU was actually the second step for me. The Walk the Walk charity, they spotted me on an application form, and I got involved with them, and they actually brought together a group of 8 men with breast cancer. And the emotion in that room, to use my French, like 8 hairy-ass men basically hugging each other to death because we were actually able to talk to people who actually understood. And I'll talk about it perhaps in another question, but and the one thing that came out of that is, have you had tamoxifen? Oh God, yeah, I hate this stuff. And we discovered that 6 out of 8 men were taking tamoxifen and have real problems with it. Now, before that time, I would never have known about it. So that, for me, was the challenge.
Thank you. Now seems a really good time to throw the opportunity to ask questions to the room. If anyone wants to ask our panel a question, please put your hand up and Steph can come round and pass around the microphone. If not, I can, okay, yeah. Thank you, Grace.
Probably for one of the Victorias. You spoke about screening, and obviously, yeah, breast cancer arises in a lot of, over 50s, postmenopausal, but a lot of younger women get it. And a lot of younger women would rely on self, checking. How much do you think that is contributing to, secondary breast cancer? Because if it's not being detected at the earlier stages, these younger women are maybe more likely to get secondary disease, because I know there's a lot more awareness on self-checking and things, but still not everybody does it, and you can't speak to everyone. So is it something that should be in schools or something like that? I don't know.
That's a great question, and it's really great to be able to clearly say that screening only works for people who are 50 and over, because it's a blunt tool in people who are younger women, because it's mammography is an X-ray of the breast, isn't it? It shows black, white, and every shade of grey, and that's how it is interpreted. The youthful breast is more dense, so purely it would show up all white. So that's why we don't routinely, use mammograms on younger women, because it would be a small amount, albeit, of radiation, and it would be useless. We use other things. MRI scans, we're more clever, for people with family histories. But you're absolutely right. It's the awareness. It's that teachable moment. I'm also on the medical advisory group for Copperfield, and that's the charity who are 16 to 24-year-olds, yes, who are trying to raise awareness of being breast aware, reporting anything that's abnormal straight away to the GP. And yeah, you're absolutely right. Sometimes we see breast cancer in the younger. The average is in the postmenopausal women in the UK. Average for menopause is 50, 51. So yeah, that's right. Bangs on that. So yes, it's getting to the younger women. In Breast Awareness Month, we have, don't we, the pink tsunami, cake sales. Everything's pink, and we can try to reach pockets of people with that. So it is breast awareness. And using those teachable moments, really.
Yeah, I think as well, again, I'm not a medical expert in this, but that awareness, my business head's just kind of clicked in, but that removing the stigma, that the scariness of it, it's a scary thought. So I think people don't check, because what if I do find something that might be scary? So it's about how do we communicate that that's okay, and that there is everything that I've learned today, I've learned so much today, actually, that there is treatment and there is hope, and hopefully a cure one day. I think it would give people that confidence to check and to remove that stigma, and definitely the move towards awareness, which I think we're on track with that as well.
Thank you.
I just want to say thank you, because what you've just discussed is amazing from the perspective of a patient. And on my professional hat, I am a marketer because I teach at the business school. So what I find interesting in everything that you said is that you're shown a role for us to try to understand the patient more, and where expertise outside of the medical field might be helpful. And just to add to that, I'm finding super interesting that as part of my career, I was always interested in researching the creative industries. And now I have found collaborations with colleagues who are filmmakers that did documentaries about breast cancer, that they want to use it to promote awareness in underrepresented groups, or artists that do VR experiences where they feature also male voices to try to raise awareness of these. So it's almost like the question that I want to ask is, do we need to think outside the box of the leaflets, of the thousands and thousands of letters that we receive, to try to reach the people that are most in need, and avoid them ending up trusting the guys that said, don't do chemo because you can heal without it?
We would like to take that one.
I'll take a hit for the team. But I think yes is the answer. The average educated person that lives in North Oxfordshire, they will go to the screening. They will come in. It's the people that don't live in North Oxfordshire that will need to be reached. And yes, we need to look for alternatives. The system works to some extent, so I think it's good to continue with the current system, but we need to also be finding for the underprivileged or underrepresented minorities. We know that many minority patients will not be doing as well. Usually it's a later presentation, it's a larger cancer, more aggressive cancer. So yes, you're right. I think we benefits. I think the problem sometimes in the system is that you need a lot of people to sit together, scratch their heads together to find how they can target these people. But there's no, not money in the sense of money, but there's no time for these people to sit together because these people are probably too busy trying to treat the people that are already coming through the system. So the system is stretched. But you're right, that's what we need to be doing.
Thank you.
Hi. Yeah, I've been really impressed today by the kind of novel ways forward, the research that against breast cancer support. So thank you for selecting presenters for that. I have a question. I think it's probably for you, Dr. Lord. You know, we've heard a lot about vaccines and immunotherapy, etc. Can you envisage a day where chemotherapy will be out of the picture?
Yes. At the moment, we're already starting to use much more in the way of targeted chemotherapy in the clinic, particularly for the treatment of advanced breast cancer, but it's going to move more and more into the treatment, we think, with regards to the early breast cancer. And we're also much better already at selecting patients for chemotherapy. So we have genetic tests, for example, receptor positive are going to benefit from chemotherapy or not, which means that a lot of women who originally used to get chemotherapy, just based on whether they had a lymph node involved, for example, don't get it now. And that's a change we've seen in the last 5 years. With regards to the these new drugs, we call them antibody drug conjugates. Essentially, they're things like the Herceptin, for example, which are attached to chemotherapy and drag that chemotherapy to where the cancer is, but not to where your other cells are. These drugs are often better tolerated and also more effective. And there's some big clinical trials going on now with a view to using these drugs instead of chemotherapy in patients with early breast cancer. And the hope is that they'll be, well, they are better tolerated and hopefully they'll also be more effective. So it may actually not be that long before we stop using standard chemotherapy for the treatment of certainly early breast cancer at any rate.
Thank you very much. I think, Mark, we may have time for one more question. If there is a question in the room, Mr. Fleming.
Thank you. One for the panel. Today's Daily Telegraph states that cancer care in the UK is about 20 years behind the rest of Europe. So it's a three-part question. The first part is that a fair characterisation? The second part is, what effect does that have on healthcare professionals? And the third part is, what effect does that sort of statement have on breast cancer patients?
Vicky, you look like you might be keen to answer.
Remind me what the statement was?
Behind Europe.
That's probably true.
I mean, well, it's going to be all right then, because we can hopefully catch up the curve, isn't it? We're doing a lot, I suppose, with genomic assays, and as we were just hearing, sharpening the tool and personalising treatment, not giving so much chemotherapy, not giving everything to everyone. That we're looking at what we've got in our armoury, being selective, and I think we're getting better at that, and perhaps we were slower. Are our processes slower than Europe in the way of take some time, don't they? Are we also dovetailing our support structures? Is that also behind? We meaning the diagnostics. We're doing a lot more interventional things. Kerry, you mean?
I definitely would agree with that in terms of maybe psychological mental health. We're hearing much more about that in recent years. But it was definitely thought of previously as the two being kind of distinct from one another. So your physical health care and your mental health, actually, they need to be, as a collective, the care needs to be holistic. And I would argue that we are lagging behind on that. I think to answer the other two parts of your question, I think that must be incredibly challenging. Actually, we were talking about this only earlier when we were kind of having coffee in the other room. For a health professional to come away from their job every day thinking that they're giving substandard care, thinking that they're not perhaps meeting patient needs in the way that patients want or expect, that must be incredibly draining. And the chances are that those are the people that step away from the profession because it eats at them. They're the very people that you need in that line of work, which is a real shame. In terms of the patients, I think to read information like that really probably isn't helpful. The only comparison I can draw, having not had breast cancer myself or a cancer diagnosis, I have recently had a baby, and there's been an awful lot of information in the media about how poor UK maternity services are versus other countries. That wasn't great to read when I was pregnant. I didn't want to hear that my care that I was potentially going into was going to be life-threatening or challenging, or I might not get the support that I need. And I imagine, without putting words into patient mouths, it must be fairly similar.
Yeah, I think it's quite a scary thing to read that. But I can only speak from my own personal experience of cancer care in the UK, which has been absolutely fantastic. I trust my medical professionals. I trust the work that you do fully. I think a scope for improvement is in this kind of collaboration and communication and being patient-centric, that part of communication part that I think, Maria, you were talking about over there. I think we can get creative. Telling stories, you know, people relate to a personal story, so our ability to do that kind of thing. And I know that during COVID, I had a whole exercise plan with a personal trainer that wouldn't have happened pre-COVID because it happened online. And my oncologist said this wouldn't have happened, but because of COVID, it is happening. So things that we can do to push that system that as a patient seems a little bit rigid sometimes, I think we can get creative in terms of the ways that we do that, and the use of modern technology and modern communications can really help with that. Yeah, thank you.
Thank you. I don't believe that statement. It's a very catchy phrase, but actually having relatives in Greece, having had patients with relatives in Spain and Italy, the things that I have heard about communication with patients being absolutely awful, surgical options not being available, treatments, patients actually having to wait at the pharmacy to pay for their chemotherapy drugs to then take them to the hospital so they can have them. I don't know where that has come from. Maybe there are some certain hospitals in Europe that can offer an amazing sort of service, but we also need to remember that everything is free here. There is a balance. I'm sure that some centers in the States are offering a better service, but everyone is paying hundreds of thousands of dollars of their lifetime to their insurances. Certainly from the surgical point of view, all the UK surgeons are trained phenomenally well compared to other countries. And I think the most important thing is that we've got a functioning MDT. People abroad go to an MDT to just actually discuss their case, but basically the professor has said this, and this is what happens. Here, if I say something and Simon disagrees, he will tell me at the meeting, well, no, actually, I don't think that surgery first is the right way forward because we can offer this. And there will be that discussion in front of 35 people, and we can work out what we all collectively think is the best thing for the patient. I don't think that happens all the time in Europe. It hasn't happened many times in my experience. So I don't want people to be disappointed by hearing a statement like this. I think it's really, really harsh. Can we be better? Yes. we've had surgery. Our current waiting is about 4 to 6 weeks for cancer surgery. Radiotherapy used to be about 6 to 8 weeks. It has come down. So yes, but there's not enough theatre time. There's not enough oncology clinic time or surgical clinic time. We can improve.
I might as well add something. So I think cancer services have been relatively protected. Maybe we don't necessarily feel that, but compared to some other services in the NHS, I can tell you that there are many European countries, Ireland, for example, which is a wealthy country, Spain, that do not have the same access to cancer drugs in the public health services. So that is definitively the case. I think that there is quite a lot of regional variation in the UK, and so what you will see in Oxford and Southampton with Ramsey and Co is not necessarily what you'll get in other parts of the UK where they struggle, and a lot of that is not down to necessarily always resource. It's about recruiting really good people and so on, to be honest, which can be very difficult in certain parts of the country. But I know that's exactly the case. The same problem exists. Having spoken to my French colleagues and so on, that if you're in Paris, great service. Elsewhere, they just can't get the staff. So these aren't just problems for the UK. They're the same elsewhere.
Thank you, and thanks for all your questions, and a massive thank you to our panel. It's been really insightful and amazing to get your insight on everything that you've helped us with today. So thanks ever so much.
Good afternoon. I want to send a special message today in celebration of our research family. I hope you've had a fantastic day, and I feel I must thank all of those who've made today possible, especially Mark, our new research manager, who has brought everything together today. Obviously, Oriel College for hosting our event, and all our researchers who are doing such a fantastic job to advance our knowledge on breast cancer treatment, diagnosis and prevention. I'd also like to obviously thank all our supporters, our fundraisers, our staff and our trustees, all the people that make what we do possible. And finally, I'd just like to emphasise the importance of what we do. We're now on a very good path with our core research programme at Southampton and all our seed-funded projects, so that we're looking to advance our knowledge on treatment, prevention and diagnostics. We're also delighted to be working with Oriel College on our fellowships, which will develop future researchers who can go on and make even greater advances on breast cancer research. So thank you very much, and hopefully you'll have a nice journey home. Thank you.